Hello and welcome to Sleepy Science. Before you drift into tonight's journey, take a slow look around the room you're in. The chair supporting you, the phone in your hand, the walls around you, they all seem solid, familiar, and completely ordinary. But according to modern physics, almost everything you are looking at is built from invisible fields, empty space, and quantum rules that your senses were never designed to notice. The world feels stable only because your brain experiences the final result, never the astonishing machinery hidden underneath. Tonight, across 30 calm and fascinating chapters, we'll uncover the strange quantum reality quietly shaping every object you touch, every color you see, every light that reaches your eyes, and every piece of technology you use without a second thought. By the end of this journey, the ordinary world may never feel quite so ordinary again. Before we begin, let me know in the comments where you're listening from and what time it is there. And if you enjoy relaxing science that gently changes the way you see reality, don't forget to like the video and subscribe. Now let the noise of the day slowly disappear, and together, let's step beneath the quiet surface of the world you thought you knew. Why solid objects feel solid if atoms are almost empty? The most solid thing in the room is held together by rules you cannot see. Rest your hand on a table and it answers with resistance. Press harder and it presses back, so naturally that the surface seems packed, continuous, and completely full. Yet if you could enlarge one of its atoms until its nucleus were the size of a small seed, the surrounding region where its electrons are found would extend far beyond it, leaving an astonishing amount of apparent emptiness between the center and the outer limits of the atom. This does not mean the table is secretly hollow like a box, because atomic emptiness is not ordinary empty space containing miniature gaps through which larger objects could simply slip. An atom is better understood as a compact system of fields, energy, and probability, with electrons spread through regions described by quantum mechanics, rather than sitting at fixed points like tiny beads. When your hand approaches the table, the electrons in your skin begin interacting with the electrons in its surface. Because they carry the same electric charge, these electron clouds strongly resist being forced into one another, creating electromagnetic forces that push back against your hand. But there is another, even deeper rule involved. Electrons belong to a family of particles that cannot all occupy exactly the same quantum state. This principle, known as the Pauli exclusion principle, prevents matter from being compressed without limit and helps atoms maintain their structure. As the electrons in your hand are brought close to those in the table, quantum rules make further overlap increasingly difficult, and the combined resistance becomes what your nervous system interprets as firmness. The sensation of solidity, then, does not come from atoms being tightly packed like grains of sand with no gaps between them. It comes from invisible interactions that become extraordinarily strong at very small distances. The nucleus provides nearly all the atom's mass, but it is the much larger electronic structure around it that determines how atoms meet, bond, and resist compression. This is why a wooden table, a metal spoon, and the bones in your hand can all feel solid, even though their atoms contain large regions without ordinary matter. Their solidity is not an illusion, but it is different from the simple picture your senses suggest. What feels like a continuous surface is really the large-scale result of countless quantum interactions happening too quickly and too consistently for you to notice individually. Even the hardness of different materials emerges from how their atoms are arranged and how strongly their electrons bind them together. Diamond resists deformation because its carbon atoms form a rigid three-dimensional network of strong bonds, while softer materials allow their atomic structures to shift more easily under pressure. In both cases, the feeling beneath your fingers is created not by tiny pieces physically touching in the everyday sense, but by forces and quantum restrictions, preventing one structure from passing freely into another. You are therefore supported every moment by something stranger than solid substance, an organized refusal. The floor holds you because its atoms resist being rearranged by yours. The chair carries your weight, because its electronic structure responds to pressure and distributes that pressure through its material. The world feels stable because these microscopic rules repeat with almost perfect reliability across unimaginable numbers of particles. And perhaps this is the quiet lesson hidden inside every ordinary object. Reality does not need to be densely filled to be dependable. A thing can be mostly open at the atomic scale and still become firm enough to build homes, mountains, and living bodies. Solidity is not the absence of space. It is space governed by structure. It is matter maintaining its shape through electric forces, quantum limits, and patterns of bonding that remain invisible while supporting everything visible. So when you place your hand on a table, you are not discovering that nature is made from perfectly packed material. You are feeling the boundary created when two vast atomic systems approach each other and the laws of physics calmly refuse to let them merge. The table feels solid, not because its atoms contain no emptiness, but because what occupies that apparent emptiness is governed by rules powerful enough to hold up your entire world. Your table is mostly empty space. The table in front of you looks like one continuous object, but if your eyes could descend far enough into its structure, that smooth surface would dissolve into a landscape so open that the word solid would begin to feel misleading. A table is built from molecules. Molecules are built from atoms. And inside each atom, the nucleus occupies only an extraordinarily small central region compared with the full space associated with the atom. Nearly all of the atom's mass is concentrated inside that tiny nucleus. While its electrons are described not as hard little spheres filling the surrounding volume, but as spread out quantum states that tell us where an electron may be detected. This means that the familiar material of the tabletop is not packed from edge to edge with miniature chunks of substance. On the atomic scale, most of its volume contains no nucleus and no electron sitting at a definite point. Yet calling this region nothing would also be inaccurate. It is crossed by electromagnetic fields shaped by the quantum states of electrons and governed by physical laws that determine how the atom can behave. The emptiness inside an atom is therefore not like the vacant air inside an unused room. It is more like a structured arena in which measurable possibilities, forces, and energy are present, even when no particle is found at one precise location. This becomes easier to imagine when you compare size rather than appearance. If an atom were enlarged until it filled a large stadium, its nucleus would be a tiny object near the center, while the region occupied by its electron states would stretch across the much larger arena. The exact comparison varies between atoms, so no single everyday model is perfect. But the central lesson remains. The visible size of matter comes mostly from the spatial reach of its electronic structure, not from the size of its dense nucleus. Now consider how many atoms exist in even a small section of wood. There are far more than your mind can picture, arranged in cellulose fibers, lignin, moisture, minerals, coatings, and countless molecular patterns created by the tree's growth and the table's manufacture. At your scale, these structures blend into a stable surface. At the atomic scale, however, the table is not a miniature version of itself. There are no tiny wooden boards hidden inside the wood. There are nuclei separated by distances enormous relative to their own size, surrounded by quantum states that overlap and form chemical bonds. Even the grain you see is an emergent pattern created by biological cells and molecular architecture, not a fundamental feature of matter. This reveals something important about scale. Properties that seem obvious in the everyday world can disappear when you look deeply enough. Smoothness, shape, hardness, and color belong to the organized whole, while individual atoms possess none of these features in the way you experience them. The table is real, but its reality is layered. One description says it is a piece of furniture supporting a cup. Another says it is a network of fibers and molecules. Deeper still, it is a collection of atomic nuclei and electrons governed by quantum laws. None of these descriptions cancels the others. Each becomes useful at a different level. And perhaps that is the strangest truth resting quietly beneath your hands. The world does not need to be filled with dense substance in every microscopic region to form something stable and familiar. What you call an object is not simply a block of material occupying space. It is a long-lasting arrangement, a pattern maintained across time, built from components whose internal scale is dominated by openness. Your table is mostly empty space, but that emptiness is organized so precisely that it can become a surface, hold a book, carry years of scratches, and remain recognizably itself. The ordinary world may look completely full, yet beneath its calm appearance, matter is shaped as much by the spaces within it as by the particles it contains. A wall is not as impassable as it looks. A wall seems to divide reality into two absolute regions, this side and the other, but nature does not recognize that boundary as completely as you do. To your body, the wall is an obstacle because the enormous collection of atoms in your skin cannot pass through the organized material without breaking bonds, displacing matter, and requiring an impossible concentration of energy. Yet the wall is not equally closed to everything. Turn on a radio in the next room, and electromagnetic waves may cross the barrier with enough strength to carry music through it. Speak loudly, and part of your voice reaches the other side, not because air travels directly through the solid surface, but because pressure waves make the wall vibrate, allowing a weakened pattern of motion to continue into the neighboring air. Heat also crosses it as energy moves through the material, while certain forms of radiation can penetrate much farther than visible light. X-rays pass through soft tissue more easily than bone because different materials absorb them by different amounts. Gamma rays can travel through even denser matter, though thick layers of heavy material may gradually reduce them. And at this very moment, an almost unimaginable number of neutrinos are moving through walls, buildings, the ground beneath you, and even your body with barely any interaction at all. These ghost-like particles are produced in places such as the sun and nuclear reactions, and because they respond extremely weakly to ordinary matter, an entire planet is often less like a barrier to them than a thin mist. This reveals that impassable is not a permanent quality belonging to the wall itself. It is a relationship between the wall and whatever is trying to cross it. Visible light is stopped or scattered because its energy interacts strongly with the electrons and structures in many opaque materials. Radio waves, with very different wavelengths, may pass through some walls while being reflected or absorbed by others. A sheet of metal can block signals that move easily through wood or plaster, and water-rich materials can absorb certain frequencies more effectively than dry ones. The wall therefore acts less like a universal gate and more like a selective filter, allowing some disturbances through, weakening others, and stopping only those that interact with its structure in particular ways. At the quantum scale, the idea of a perfectly sharp barrier becomes stranger still. Particles are represented by quantum states that can extend into regions classical physics would forbid, and under certain conditions, there is a small probability that a particle will appear beyond a barrier without crossing it in the ordinary step-by-step sense. This process is called quantum tunneling, but it does not mean a human being could casually walk through concrete. For a large object, countless particles would need to tunnel together while preserving the exact arrangement of the body, and the probability is so fantastically small that it has no practical meaning. The distinction matters because quantum physics does not make every imagined event likely. It describes probabilities, and most macroscopic possibilities are suppressed so severely that the everyday world remains dependable. Still, the wall is more active and permeable than its silent surface suggests. Its atoms vibrate with temperature, energy enters and leaves it. Sound shakes it, fields extend through and around it. Invisible particles pass through it, and microscopic processes occur within it continuously. Even the boundary you see is not perfectly exact, because the outermost atomic and electronic structures do not end along a mathematically sharp line. The clean edge is a useful picture created at human scale, where all those subtleties blur into a flat surface. This does not make the wall unreal or weak. It means its strength is specific. It is very good at resisting objects like you, while remaining almost transparent to certain parts of the universe. You could spend your whole life treating walls as symbols of final separation, yet physics quietly shows that no ordinary boundary is closed in every possible sense. Light may fail where radio succeeds. Matter may stop your hand while neutrinos ignore it. Sound may fade, but still leave a trembling trace on the other side. The wall does not separate two worlds completely. It changes what can travel between them and how much of the original signal survives. And perhaps that is the more accurate way to understand many boundaries around you, not as perfect endings, but as regions of transformation, where some patterns are blocked, some are altered, and others pass through, almost as though the barrier had never been there. Electrons do not orbit like tiny planets. The picture of an electron circling an atomic nucleus, like a tiny planet, is one of the most familiar images in science, and one of the most misleading. It appears in school diagrams, animations, logos, and even jewelry, because it gives the atom a shape the mind can understand. A central nucleus acting like a miniature sun, with electrons traveling around it in clean circular paths. But real electrons do not move through atoms that way. The planetary model was useful for a short time because it helped scientists explain why atoms emit particular colors of light. Yet it could never describe the full behavior of matter. A charged particle moving in a classical orbit should continuously lose energy, spiral inward, and crash into the nucleus. If electrons truly behaved like tiny planets, stable atoms would not last. Chemistry would collapse, and the ordinary world would be impossible. The fact that atoms remain stable was one of the clues that nature was following rules far stranger than ordinary motion. In quantum mechanics, an electron inside an atom is described by a wave function, a mathematical description that gives the probabilities of different measurement results. This does not mean the electron is secretly following a normal path that scientists simply cannot see. Experiments show that the idea of a definite hidden orbit is generally the wrong starting point. Before a position is measured, the electron is represented by a state spread across a region around the nucleus. Scientists call these regions orbitals, but an orbital is not an orbit. An orbit is a path. An orbital is a pattern describing where an electron is likely to be detected and how its quantum properties are arranged. Some orbitals form roughly spherical distributions. Others have two lobes, several lobes, rings, or more complicated shapes. These forms are not decorative guesses. They emerge from the allowed quantum states of electrons under the electrical attraction of the nucleus. The shapes also influence how atoms bond, which directions molecules take, and why substances develop particular chemical properties. The geometry of water, the strength of carbon-based structures, and the behavior of oxygen all depend in part on the arrangement of electron orbitals. Yet even these cloud-like images require care. The shaded regions in diagrams are not physical fog surrounding the nucleus, nor do they show an electron smeared like paint across space in an ordinary material sense. They are visual maps of probability. If you repeatedly prepared the same atom and measured the electron's position, the results would gradually form a pattern matching the orbital. Each individual measurement would locate the electron somewhere specific, but the complete collection of results would reveal the spread predicted by quantum theory. This is why asking, where exactly is the electron while no measurement is being made, may not have the kind of answer you expect. Quantum mechanics does not always assign an electron a precise position and a precise motion at the same time. The uncertainty is not merely caused by weak microscopes or clumsy instruments. It belongs to the structure of the theory and has been confirmed through countless experiments. An electron in an atom can possess a well-defined energy state without possessing a tiny circular root. This is one of the deepest changes quantum physics made to our picture of nature. An object can have real, measurable properties while refusing to fit into the familiar story of a small body tracing a continuous path. The energy states themselves are also restricted. An electron bound to an atom cannot take any energy it wishes, just as a vibrating string cannot produce every possible pattern at once. Only certain stable quantum patterns are allowed. When the electron changes from one permitted state to another, the atom must gain or release a precise amount of energy. That energy may be exchanged as a photon, producing specific lines of light that act like fingerprints for different elements. Astronomers use these spectral fingerprints to identify the composition of distant stars, even though those stars may be separated from Earth by enormous distances. In this quiet way, the fact that electrons do not orbit like planets allows light to carry chemical information across the universe. There is still a kind of angular momentum associated with atomic electrons, which is one reason the old orbital language can seem tempting. But quantum angular momentum is not simply a tiny ball moving around a track. It comes in permitted amounts and follows rules with no exact everyday equivalent. The same is true of electron spin. Despite the name, spin does not mean that the electron is literally rotating like a miniature globe. It is an intrinsic quantum property that affects magnetism, atomic structure, and the way electrons can share available states. The vocabulary of quantum physics often borrows familiar words: orbit, spin, cloud. But the reality behind those words is less mechanical and more abstract than the images they suggest. This does not mean atoms are unknowable. On the contrary, quantum theory predicts their behavior with extraordinary accuracy. It explains the periodic table, chemical bonds, electrical conductivity, lasers, semiconductors, and much of modern technology. What it asks you to surrender is not understanding, but one particular kind of understanding. The belief that everything must behave like a scaled-down object from daily life. The electron is not a tiny marble, not a hidden planet, and not a speck wandering through a hazy shell. It is a quantum entity whose state contains possibilities, energy patterns, and measurable relationships that cannot be reduced to a single classical picture. When you see the familiar atomic symbol with neat rings around a central point, you are looking at a historical shortcut, not a photograph of reality. The real atom is less like a miniature solar system, and more like a set of standing possibilities organized around a nucleus, each state constrained by rules that determine where the electron may be found, what energy it may have, and how it can interact with other atoms. This may feel less visually satisfying than a planet following a clear path, but it reveals something far more important. Nature is not required to arrange itself in forms that human intuition evolved to recognize. Your mind prefers trajectories, locations, and moving objects because those ideas work well at your scale. Deep inside matter, however, reality is built from states and probabilities that become definite only in particular interactions. The electron does not fail to behave like a planet because our picture is incomplete. It behaves differently because the universe is not a miniature version of the world you can see. And once that old image fades, the atom becomes not emptier or less real, but more remarkable. A stable structure created without tiny worlds circling tiny suns, held together instead by quantum patterns that have quietly shaped every molecule, every living cell, and every element you have ever known. Your phone screen glows because electrons fall between energy levels. Every image on your phone begins with an invisible drop of energy. The face on the screen, the blue of a distant ocean, the red glow of a notification, and the white shape of a sentence all appear because electrical energy is being converted into carefully controlled packets of light. But the exact process depends on the kind of display you are holding. In a modern OLED screen, each tiny picture element produces its own light, while in an LCD screen, the picture is shaped from light supplied by a separate LED backlight. Both technologies ultimately depend on electrons changing their energy within specially designed materials. But an OLED display reveals the quantum process most directly. Beneath the smooth glass are millions of pixels, and each pixel is divided into smaller red, green, and blue subpixels. These subpixels are so small that your eyes normally cannot distinguish them. Instead, their light blends together, creating the colors and details you perceive as a single continuous image. Inside an OLED subpixel are thin layers of organic semiconductor material. Here, organic does not mean natural or biological. It refers to carbon-based molecules engineered to carry electrical charge and emit light. When the phone applies a voltage, negative charges and corresponding positive charge carriers are pushed into the material from opposite sides. When they meet, the system can enter an excited state, meaning energy has been stored within the electronic structure of the molecule. That excited arrangement is not usually permanent. As the material returns to a lower energy state, the lost energy can leave as a photon, a single quantum of light. The photon's color depends largely on the size of the energy difference involved. A larger energy gap can produce a higher energy photon toward the blue part of the visible spectrum, while a smaller gap can produce lower energy red light. The molecules in each subpixel are therefore selected and engineered so that their allowed electronic transitions generate a chosen range of colors. Your screen does not begin with white light and paint it red or green in the ordinary sense. In an OLED display, the material itself releases photons with energies that your visual system later experiences as color. Brightness is controlled mainly by changing how much electrical current passes through the subpixel. More recombination events generally mean more photons and therefore a brighter point of light. When a region of an OLED screen displays true black, its subpixels can simply remain off, producing almost no light at all. This is why OLED screens can create deep blacks and strong contrast, and why a mostly dark interface may use less display power than a bright white one. Yet the process is not perfectly efficient. Some electrical energy becomes heat rather than visible light, and the light-producing materials gradually age. Blue-emitting compounds have historically been especially difficult because producing blue light requires relatively energetic transitions, and the materials can degrade faster under that demand. Uneven aging can eventually contribute to image retention or permanent burn-in, particularly when the same bright shapes remain in fixed positions for very long periods. Engineers reduce this through improved materials, pixel shifting methods, brightness management, and software that adjusts how the display is driven. An LCD phone follows a different route. Its pixels do not normally emit their own light. Behind them is a backlight, usually made from LEDs, where electron transitions in semiconductor materials generate light. That light then travels through filters and layers of liquid crystals. By changing their orientation under an electric field, the liquid crystals control how much light passes through each red, green, or blue filter. In this case, the quantum light source sits behind the image, and the pixels behave more like millions of adjustable shutters. This is why an LCD often cannot create perfect black. Even when a pixel tries to block the light, a small amount may still leak through from the active backlight. OLED and LCD screens may look similar from the outside, but they construct darkness in opposite ways. One creates black by producing no light at that location. The other creates it by trying to block light that is already present. The display must also refresh rapidly, rewriting the brightness of millions of subpixels many times each second so that motion appears smooth. Nothing actually travels across the glass when an icon slides from one side to the other. Instead, one group of pixels dims while neighboring groups brighten in carefully timed succession. Your brain joins these separate updates into continuous movement, much as it turns a sequence of still frames into a film. The picture feels stable, yet it is being reconstructed moment after moment through electrical instructions sent to microscopic regions of material. Even white is not a single substance hidden inside the screen. It is usually created by combining red, green, and blue light at suitable intensities. Yellow can emerge from red and green. Cyan comes from green and blue. Purple appears when red and blue reach your eyes together. By varying only 3 primary channels, the display can produce millions of color combinations, although the exact range depends on its materials, calibration, brightness, and design. The screen is therefore not storing tiny copies of the colors found in the world. It is generating patterns of photons that stimulate the color-sensitive cells in your eyes in ways similar to the light arriving from real objects. A digital sunset contains no warm air, no distant horizon, and no actual setting sun. It is an ordered stream of red, green, and blue photons, whose proportions persuade your visual system to build the experience of a sunset. This makes the phone screen a remarkable meeting point between quantum physics and perception. At one end, electrons and charge carriers move through materials whose allowed energy states have been engineered with extraordinary precision. At the other, your retina absorbs the released photons and converts them into signals that the brain interprets as shapes, faces, depth, and color. Between those two ends lies the entire visual world of the device. The screen seems like a window, but it is really a controlled field of microscopic light sources, each one responding to instructions, each one turning electrical energy into a small luminous event. And perhaps the strangest part is how completely the machinery disappears from your awareness. You do not normally see electronic transitions, subpixels, filters, or rapidly changing brightness values. You see a message from someone you miss. You see a map leading you home. You see a photograph preserving a moment that no longer exists. The physics remains hidden because it works so well. Yet every glowing image is built from brief releases of energy, repeated millions of times and arranged with such precision that quantum events become pictures, movement, and meaning. The light in your hand is not a miniature world trapped beneath glass. It is matter repeatedly changing state and giving part of its energy to the darkness as photons, while your mind quietly turns those photons into a world. Glass is transparent for a quantum reason. A window performs a quiet trick every time daylight passes through it. It allows visible light to enter while refusing to be equally open to many other forms of energy. And the reason lies not in the glass being empty, thin, or weak, but in the quantum structure of its electrons. At first glance, transparency seems simple. Light reaches one side of the pane and emerges from the other. So it is tempting to imagine that photons merely slip through gaps between atoms. But that picture is wrong. The atoms in glass are far smaller than the wavelengths of visible light, and the material is not transparent because it contains straight microscopic tunnels. Light crosses glass because most visible photons do not carry the right amount of energy to be permanently absorbed by its electrons. Inside every material, electrons are allowed to occupy certain ranges of energy, while other ranges are forbidden. In glass, especially common silica-based glass, the occupied electronic states are separated from the next available states by a relatively large energy gap. A visible photon usually carries too little energy to lift an electron across that gap. The photon cannot simply give the electron part of what it needs and disappear, because quantum interactions require the energy exchange to match an allowed transition. If the photon does not fit one of the material's available electronic changes, it is unlikely to be absorbed in that way, so the light continues through. This is one of the most important ideas hidden inside transparency. Matter does not absorb every kind of light merely because light strikes it. Absorption is selective. The photon must arrive with an energy that the material can actually accept. Visible wavelengths happen to fall within a broad region where ordinary window glass absorbs relatively little, which is why you can look through it and see the world beyond. But change the wavelength, and the same pane behaves differently. Ultraviolet light carries more energy, and some ultraviolet photons can trigger transitions or interact with impurities that visible light cannot. So ordinary glass blocks a significant portion of ultraviolet radiation. Move in the other direction toward parts of the infrared spectrum, and the vibrating bonds within the glass can absorb energy more effectively, making the material less transparent to certain heat-related wavelengths. The window is therefore not universally transparent. It is transparent only within particular ranges, and your eyes happen to be sensitive to one of them. This coincidence is not entirely accidental from the perspective of life on Earth. The sun delivers a large amount of its energy in and near the visible range, and Earth's atmosphere also permits much of that light to reach the surface. Human vision evolved within this available window, so the radiation that glass passes and the radiation you call light overlap in a way that makes transparency feel like a basic property. Yet to an instrument sensing different wavelengths, the same sheet of glass might appear dark, reflective, or opaque. Even while visible light passes through, it does not move through glass exactly as it moves through empty space. The electric field associated with the light disturbs the charged particles in the material, especially the electrons, causing them to respond collectively. The incoming wave drives tiny oscillations, and those oscillating charges generate their own electromagnetic response. The combined effect causes the light's progress through the material to be slower than it would be in a vacuum. This does not mean individual photons are simply flying normally and repeatedly stopping for rests. It is better understood as light interacting continuously with the material, producing a combined pattern whose overall propagation is delayed. When the light leaves the glass, it resumes its usual speed in the surrounding air or vacuum. This change in propagation is also why light bends when it enters a pane at an angle. One part of the wave enters the slower medium before another part does, changing the direction of travel. Refraction, the bending that makes a straw appear displaced in a glass of water or causes a lens to focus an image, is therefore connected to the same electronic response that allows transparent materials to guide and reshape light. Transparency does not mean absence of interaction. It means interaction without strong absorption. The light and the material influence each other, but most of the visible energy survives the passage. Some photons are still reflected at the surface, which is why you may see your own faint image in a dark window. The amount reflected depends on the difference between how light propagates in air and how it propagates in glass, as well as the angle at which it arrives. Other photons may be scattered by scratches, bubbles, dust, microscopic irregularities, or chemical impurities. Perfect transparency is therefore an ideal. Real glass always absorbs, reflects, and scatters a small fraction of the light. The clearer the glass appears, the more carefully its composition and internal structure have been controlled. Its atomic arrangement matters as well. Ordinary glass is an amorphous solid, meaning its atoms are connected without forming the long repeating order of a crystal. This disorder does not automatically make it transparent. Many disordered materials are opaque. What matters is whether the material's electronic structure avoids absorbing visible wavelengths and whether its internal variations are small enough not to scatter visible light strongly. If regions inside the material differed significantly over distances comparable to visible wavelengths, light would be scattered in many directions, producing a cloudy appearance. This is why frosted glass is still chemically glass, but no longer provides a clear view. Its roughened surface scatters light, preserving brightness while destroying the organized directions needed to form an image. You can tell that light is present on the other side, but you cannot reconstruct where each ray came from. Transparency, then, requires more than transmission. It requires the light's spatial information to survive. A clear pane preserves enough of the incoming directions for your eyes to build an image, while translucent glass allows energy through but scrambles the pattern, adds certain metal ions or nanoparticles, and glass can become colored because those additions introduce new allowed interactions with selected wavelengths. Cobalt compounds can absorb portions of visible light and leave the glass looking blue. Iron impurities may produce greenish or brown tones. Gold nanoparticles can create deep reds, not because red substance is painted inside the glass, but because electrons in the particles respond collectively to particular frequencies of light. Stained glass windows are therefore records of selective quantum interaction. Some wavelengths are absorbed or redirected, while others survive and reach your eyes. The color that enters a cathedral is shaped by which energies the material refuses to pass. This also explains why transparency can change when composition changes only slightly. A material may look clear, tinted, dark, or reflective because its electron states have been altered by a small number of added atoms. The visible character of a large object can depend on microscopic changes too small for you to see directly. When you look through a window, then, you are not looking through something that light ignores. You are witnessing an extraordinarily selective negotiation. The photons interact with the charged structure of the material, slow in their collective progress, bend at its boundaries, and sometimes reflect. Yet most visible wavelengths fail to find an allowed route into permanent absorption. They emerge carrying enough of their original directional pattern for the world outside to remain recognizable. The glass disappears from your attention precisely because its quantum restrictions are so effective. It is present, active, and full of responding matter, but within the narrow band your eyes call visible light, it mostly chooses not to keep what arrives, and perhaps that is the deeper lesson hidden in every clear surface. Invisibility does not always come from being absent. Sometimes the thing becomes visually silent because the energies reaching it do not match the changes it is permitted to make, allowing the world beyond it to pass through almost undisturbed. The quantum reason metal feels cold. Metal can feel cold enough to seem as if it contains winter inside it, even when it has been resting in the same room as the wooden table beside it. Touch both objects, and the difference appears immediate. The wood feels mild, while the metal seems to pull warmth from your skin. Yet a thermometer may show that they are at nearly the same temperature. The mystery is resolved when you realize that your skin does not measure temperature directly. It senses how quickly heat is entering or leaving your body. An object feels cold when energy flows out of your warmer skin faster than your nervous system expects, and metal is exceptionally good at carrying that energy away from the point of contact. The deeper reason begins with the unusual behavior of electrons inside a metal. In many non-metallic materials, electrons remain strongly associated with particular atoms or chemical bonds. In a metal, some of the outer electrons are not confined to one individual atom. They occupy quantum states that extend throughout much of the material, forming a mobile population that can respond to electric fields and transport energy. It is common to describe them as free electrons, although they are not completely free in the ordinary sense. They still move within the repeating electrical environment created by the metal's atoms, and quantum rules determine which energy states they may occupy. This shared electronic structure is one reason metals conduct both electricity and heat so effectively. When your warm finger touches a metal surface, particles in your skin are moving and vibrating more energetically than those in the cooler object. Energy begins crossing the contact boundary. Inside the metal, mobile electrons near the surface gain some of that energy and rapidly redistribute it into neighboring regions. The energy does not remain trapped beneath your fingertip. It spreads away through the material, allowing the surface in contact with you to continue accepting more heat. Your skin therefore keeps losing energy, and its temperature falls quickly enough to activate cold, sensitive nerve endings. Wood behaves differently. Its electrons are largely bound within molecules, so they cannot carry thermal energy through the object as efficiently. Heat still travels through wood, but much of it moves through vibrations of the material's atomic structure, and that transfer is relatively slow. The thin region of wood beneath your hand warms up and then acts as a temporary insulating layer. Once that surface becomes closer to your skin temperature, the rate of heat loss decreases, so the wood stops feeling intensely cold. Metal refuses to offer the same comfort. It continually carries the transferred energy deeper into itself, exposing your skin to another effectively cooler region of material. This is why a metal door handle, stone countertop, and wooden chair can all begin at the same room temperature, yet feel strikingly different. What you experience is not simply the object's temperature, but its thermal conductivity, heat capacity, density, surface condition, and the quality of contact between it and your skin. A smooth metal surface often creates close contact over a relatively large area, which strengthens heat transfer. Rough, porous materials contain tiny pockets of air, and air is a poor conductor, so those trapped spaces slow the movement of energy. This is why fabrics, foam, feathers, and wool can feel warm even though they do not generate heat on their own. They reduce the rate at which your body's energy escapes. Metal does almost the opposite. Its structure offers heat an efficient route away from you. At the microscopic level, energy in a solid can travel in more than one way. The atoms in the material are not motionless. They vibrate around their average positions, and these coordinated vibrations can carry heat through the solid. Physicists describe the quantized packets associated with these vibrations as phonons. A phonon is not a tiny object bouncing around inside the metal like a bead. It is a quantum description of a collective vibration passing through many atoms. In nonmetals, phonons often carry most of the thermal energy. Metals have phonons too, but their mobile electrons provide an additional and often highly effective channel. The same broad electronic freedom that allows a copper wire to carry current also helps copper move heat quickly. This connection is why many excellent electrical conductors are also excellent thermal conductors, though the relationship is not perfectly identical in every material or under every condition. Copper, silver, and aluminum transfer heat efficiently because their electronic structures allow energy to move with relatively little obstruction. Stainless steel, despite being metallic, conducts heat less effectively because its mixture of different atoms disrupts the movement of electrons and lattice vibrations. This is useful in cookware. A pan may have a highly conductive aluminum or copper core to spread heat evenly, while stainless steel provides a durable cooking surface. The handle may be made from plastic, wood, or another poor conductor so that heat from the pan does not reach your hand too quickly. Everyday design quietly depends on controlling the same energy flow that makes a metal object feel cold. There is another revealing side to this effect. If the metal is hotter than your skin, its ability to transfer heat makes it feel dangerously hot for exactly the same reason it once felt cold. A metal bench in winter removes energy quickly, while the same bench under strong summer sunlight can deliver energy to your skin much faster than nearby wood. Thermal conductivity has no preference for coldness. It simply enables heat to move efficiently from the warmer region toward the cooler one. The sensation depends on which side of the temperature difference you occupy. This is why touching metal can mislead you about its actual temperature. A metal object slightly cooler than your hand may feel colder than a much cooler insulating material because the metal extracts heat faster during the first moments of contact. Your body is reading the speed of change rather than calmly waiting for an exact measurement. This rapid biological judgment is useful. It helps you withdraw from surfaces that may cool or heat tissue dangerously. But it also means touch is not a laboratory instrument. The coldness seems to belong to the metal, though part of the experience is being created by your own warmth leaving you. The sensation exists in the relationship between two systems: the thermal state of your body and the pathways available inside the material. Quantum physics enters not as a mysterious force making metal naturally cold, but as the foundation of those pathways. The electrons in a metal can occupy extended states because of how many atoms combine into a solid. Their allowed energies form broad bands rather than isolated atomic levels. And in a conductor, there are available nearby states that let electrons respond and transport energy through the material. You do not need to see these bands or follow individual electrons to feel their consequence. It reaches you as a chill in your fingertips, a cooking pan that heats evenly, a laptop frame that carries heat away from internal components, or a radiator spreading warmth into a room. The invisible organization of electrons becomes a physical sensation before you ever think about the science behind it. And perhaps that is what makes this ordinary moment so revealing. When metal feels cold, you are not detecting a hidden store of coldness. You are feeling your own energy depart through a material whose quantum structure is unusually skilled at receiving it and passing it onward. The chill is not simply inside the metal or inside your hand. It is the brief, measurable story of warmth finding an easier road. A mirror works because light behaves like a quantum object. A mirror seems to return your face instantly, as though the image had been waiting behind the glass, but nothing is stored there, and nothing inside the mirror knows what you look like. The image is rebuilt continuously from light arriving at the surface, interacting with matter, and returning toward your eyes in an ordered way. When light from a lamp, a window, or the sky strikes your face, different parts of that light are absorbed, scattered, and redirected by your skin, hair, eyes, and clothing. Some of those photons then travel toward the mirror. What happens next depends on the mirror's internal structure. An ordinary household mirror is usually not reflective because of the glass itself. The glass mainly protects a thin metallic coating, often made from aluminum or silver, placed behind it. Light first passes through the glass, reaches that metal layer, and encounters electrons that can respond collectively to the changing electric field carried by the light. In a metal, many electrons are shared across the material, rather than being permanently attached to one particular atom. When incoming light disturbs them, these electrons begin to oscillate together. Their motion creates a new electromagnetic response that travels away from the surface. On the front side of the mirror, this response combines in such a way that much of the light is sent back into the room. From a classical point of view, you can describe this as a wave driving charges in the metal and being reflected by their collective motion. From a quantum point of view, the light arrives and leaves in indivisible packets called photons, and the interaction is governed by probabilities and quantum amplitudes. These are not two unrelated stories. They are two levels of description for the same event, one emphasizing the smooth behavior of large numbers of photons, and the other revealing that the energy arrives in discrete exchanges. A single photon sent toward a partially reflective surface does not split into two smaller half-photons. It is ultimately detected as a whole packet on one side or the other. Yet before detection, quantum theory allows different possible paths, reflection and transmission, to contribute to the outcome. The probabilities depend on the material, the thickness of its layers, the photon's wavelength, and the angle at which it arrives. When enormous numbers of photons reach a normal mirror, these individual quantum outcomes form the stable reflection you experience. The familiar rule that the angle of reflection matches the angle of arrival emerges because the contributions associated with that direction reinforce one another, while many other possible directions largely cancel. The mirror, therefore, does not throw photons backward randomly. Its flat, regular surface preserves the organization of the incoming light. This is the crucial difference between a mirror and a white wall. A wall can reflect plenty of light, which is why you can see it, but its microscopic roughness sends that light in many directions. Information about where each ray came from becomes scrambled, so no clear image survives. A polished mirror is smooth on the scale, relevant to visible wavelengths. The reflected light remains orderly enough that rays arriving from one point on your face travel toward your eyes as though they had come from a corresponding point behind the surface. Your brain extends those returning paths backward in straight lines and constructs a virtual image. Nothing is actually standing behind the mirror, and light does not travel from that imaginary location. The apparent depth is created because the reflected photons reach your eyes with the same directional pattern they would have had if a real copy of the scene existed beyond the glass. This is also why the image seems to remain in place when you move. The mirror is not following you or updating a hidden picture. Each new position changes which photons reach your eyes, and your visual system continually rebuilds the scene from the latest directions. A mirror is sometimes said to reverse left and right, but that description is not quite accurate. It reverses the direction perpendicular to its surface. Front becomes back. If you raise your right hand, the image raises the hand opposite it, because you are facing a version of yourself oriented toward you. The mirror has not secretly exchanged the two sides of your body. It has returned the geometry of the light. Real mirrors also reveal that reflection is never perfect. Some photons are absorbed by the metal and their energy becomes heat. Some are lost in the glass. Some reflect from the front surface before ever reaching the metallic layer, which can create faint secondary images known as ghost reflections. Silver reflects visible light extremely well, but can tarnish when exposed to certain chemicals in the air, while aluminum is durable and reflects a broad range of wavelengths, making it useful in both household and scientific mirrors. Astronomical telescopes often use carefully coated aluminum mirrors because they must collect faint light from objects unimaginably far away. In laboratories and lasers, another kind of mirror can be made without relying mainly on a metal. A dielectric mirror contains many extremely thin transparent layers, each designed so that reflections from their boundaries reinforce one another for selected wavelengths. Light reflected from one layer returns in step with light reflected from the others, producing very high reflectivity in a narrow range of colors. The effect depends on wave interference, but it remains quantum at the level of individual photons. Even one photon can behave according to the combined possibilities created by all the layers. This is one of the most striking lessons hidden in a mirror. Quantum behavior does not disappear when light becomes part of an ordinary scene. It accumulates into the stable rules of optics. Billions of microscopic interactions become one calm image. The reflection looks continuous because your eyes receive an immense stream of photons. But each photon carries only a small fragment of information. One may have come from the edge of your pupil, another from a strand of hair, another from the fabric on your shoulder. No single photon contains your whole face. The image exists only in the pattern formed by countless arrivals and in the nervous system that assembles them into a recognizable person. If the room becomes completely dark, the mirror does not preserve a fading version of you. It shows nothing because no useful photons are returning. Its apparent power was never to create an image from itself, but to maintain the structure of light well enough for your eyes to create one. And perhaps that is why a mirror feels more mysterious the longer you consider it. You stand before a silent sheet of glass and metal, yet what reaches you is not a copy hidden in the surface. It is a reconstruction made from quantum objects that touched your surroundings, crossed the room, interacted with a sea of electrons, and returned in a precise arrangement. The face you recognize is not inside the mirror at all. It exists for a moment in the disciplined journey of light between the world, the surface, and you. You never truly touch anything. The moment your fingertip meets a surface feels so immediate that questioning it seems absurd. Yet the word touch hides a problem. At the smallest scale, neither your finger nor the object possesses a perfectly sharp outer edge that can meet another edge in the way two solid blocks appear to do. An atom has no hard shell marking the exact place where it ends. Its outer electronic state fades gradually into space. So when your hand approaches a cup, a page, or another person's skin, there is no single instant when two microscopic boundaries click together. Instead, the electrical environments of the approaching atoms begin influencing one another across a tiny distance. Charges rearrange, bonds deform slightly, and forces grow rapidly as the separation decreases. Long before the atomic nuclei could come close enough to resemble colliding balls, the interaction has already become strong enough to slow and stop the motion of your hand. In everyday language, this is touch. In microscopic language, it is a continuous exchange of forces. Saying that you never truly touch anything is therefore partly true and partly a matter of definition. If touch means that two perfectly rigid atomic surfaces make direct contact, then that event never occurs, because atoms are not miniature objects with polished outer skins. But if touch means that two bodies come close enough to exert forces, exchange energy, deform, and produce a measurable response, then you touch things constantly. Physics does not reveal that contact is fake. It reveals that contact is an interaction rather than a collision between hard edges. When you press a fingertip against glass, the skin does not remain unchanged. Its ridges flatten, soft tissue shifts, fluids move, and the contact area expands. The glass also deforms, though by an amount too small for you to notice. Forces spread outward through both materials, and the surface pushes against different regions of your fingerprint with different strengths. Specialized nerve endings inside your skin respond to this changing pressure, stretch, vibration, and motion. Some receptors react strongly when contact first begins, helping you notice a tap or a slipping object. Others continue sending signals while pressure remains, allowing you to judge shape and grip. Your brain combines these signals with information from muscles and joints, then constructs the unified sensation that something is beneath your hand. You do not directly perceive atoms interacting. You experience a biological interpretation of how your tissue is being disturbed. This is why touch can change even when the object does not. A surface may feel smooth when you move slowly across it, but rough when your finger moves faster. A faint texture can become easier to detect if it produces vibrations to which your skin is especially sensitive. When your fingers are wet, cold, numb, or softened after time in water, the same material can feel different because the mechanics of your skin and the sensitivity of its receptors have changed. Touch belongs neither entirely to the object nor entirely to you. It emerges from the meeting between a material, a moving body, and a nervous system interpreting the result. At very small separations, several kinds of interaction can contribute. Molecules can attract one another through subtle shifts in their electrical distributions, creating weak forces that help geckos cling to walls and allow fine dust to adhere to surfaces. Water molecules, oils, and contaminants on your skin can form temporary bridges between you and an object. On sticky materials, molecular chains may spread into the microscopic contours of your finger and resist being pulled apart. Friction is also more complicated than two rough surfaces simply catching like saw teeth. Microscopic high points carry much of the load. Local bonds can form and break, and tiny regions may deform or wear away as one surface slides across another. What you call rubbing is an immense sequence of molecular rearrangements, energy losses, vibrations, and broken contacts. Some of the organized motion becomes random thermal motion, which is why vigorous rubbing warms your hands. Contact can even become intimate enough for atoms to exchange or share electrons in chemical bonds. Glue hardens because molecules create connections across two surfaces. Metals can fuse when extremely clean surfaces are pressed together under suitable conditions, a phenomenon known as cold welding. In the vacuum of space, where oxide layers and airborne contamination may be absent, pieces of the same metal can bond unexpectedly because the atoms at their surfaces no longer have a clear reason to remain part of separate objects. This shows that the border between touching and joining is not absolute. Bring materials close under one set of conditions and they merely press against each other. Under another, their surface atoms reorganize until the distinction between the objects begins to disappear. Even human touch involves small transfers of material. Every time you hold a handle, you may leave behind water, skin oils, salts, microorganisms, and fragments of dead cells, while collecting traces from the surface in return. Contact is not always a clean meeting followed by separation. It can be an exchange, however small, in which each surface leaves with something from the other. This makes the familiar statement that you never touch anything less lonely than it first sounds. You are not eternally isolated behind an invisible barrier. Forces pass between you and the world. Momentum changes, heat flows, surfaces bend, molecules adhere and separate, signals travel through nerves, and sometimes matter itself is transferred. What does not happen is the simplistic event your imagination may picture. Tiny solid particles striking one another at perfectly defined boundaries. Nature replaces that crude collision with something richer, a region where interactions gradually intensify and where separate structures respond to one another without needing hard shells. When you hold someone's hand, the meaning of that moment is not weakened because atomic nuclei do not press together like stones. The warmth, pressure, changing pulse, deformation of skin, and information carried into both nervous systems are all physically real. Indeed, the experience exists precisely because distance becomes small enough for those interactions to matter. Touch is not the disappearance of all space between two things. It is the point at which the remaining separation stops being irrelevant. So the next time your fingers close around an ordinary cup, you may think of contact not as two pieces of matter finally striking, but as two organized worlds entering one another's influence. Their edges were never sharp, their meeting was never silent, and the sensation in your hand is the mind's calm summary of countless microscopic changes. You do touch the world, but nature's definition of touch is not collision, it is response. The chair beneath you is made of invisible fields. The chair beneath you looks like a collection of wood, metal, plastic, or fabric, but at the deepest level, it is better understood as a stable pattern formed within invisible fields that extend through all of space. This does not mean the chair is an illusion, and it does not mean matter is secretly made of empty ideas. It means that modern physics no longer treats particles as tiny self-contained grains, existing independently of everything around them. In quantum field theory, the basic ingredients of nature are fields. and what you call a particle is a localized excitation of one of those fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. The particles inside the atomic nuclei of the chair are also connected to deeper fields of their own. These fields are not added later as invisible forces surrounding solid objects. They are part of what the objects fundamentally are. The chair appears to be built from separate pieces because the excitations in these fields form long-lasting structures. Protons and neutrons gather into nuclei. Electrons occupy stable states around them. Atoms join into molecules, and molecules organize into fibers, polymers, crystals, coatings, and countless other arrangements. What looks like a single object is therefore a hierarchy of patterns held in place by interactions among fields. Consider a wooden chair. Its strength does not come from a vague substance called wood filling its shape. It comes from cellulose molecules bundled into long fibers, bound together with other biological materials that were once built inside a living tree. Those molecules remain stable because electromagnetic interactions determine how their electrons and nuclei arrange themselves. A metal chair follows a different architecture. Its atoms may form an ordered crystal structure, while their electrons help bind the material into a strong and flexible whole. A plastic chair is built from long molecular chains whose shapes and connections allow them to bend, resist breaking, or return toward their original form. The materials differ, yet in every case their visible properties emerge from the way field excitations are organized. The word field can sound abstract because you cannot point to one with your eyes, but you already recognize fields through their effects. A magnetic field can guide a compass without a visible thread. Earth's gravitational field changes the motion of falling objects. The electromagnetic field carries light across a room and allows electrical devices to operate. Quantum fields go deeper by suggesting that even the particles producing and responding to these effects are themselves expressions of fields. The chair is not sitting inside a universe made from one kind of material, while fields float mysteriously around it. The chair and the space around it belong to the same underlying physical framework. What changes from place to place is the state of those fields. In the region occupied by the chair, energy and quantum excitations are arranged into matter. In the surrounding air, different arrangements form gases. In a near vacuum, fields still exist even when very few particles are present. This allows you to see the chair not as an isolated block placed into an empty container called space, but as a persistent concentration of structure within a continuous physical world. Its boundaries are practical rather than ultimate. You say the chair ends at its surface because that is where its material density changes sharply, and where its behavior becomes different from the surrounding air. Yet its influence does not stop there. The chair produces a tiny gravitational effect because it has mass and energy. Its electrical charges create fields that mostly cancel at large distances, but become important nearby. It emits infrared radiation according to its temperature, sending energy outward into the room. It absorbs light, reflects certain wavelengths, and exchanges heat with the air. Even when it appears completely still, it remains connected to its surroundings through fields and energy transfer. The chair is not a sealed object. It is a stable region participating in a larger network. When you sit down, your weight changes that region. The material bends by a small amount, even if you cannot see it. Internal stresses spread through the seat, legs, joints, and floor. In physics, stress is not merely a word for psychological tension. It describes how forces are distributed within a material. Some regions are compressed, others are stretched, and the structure settles into a new balance. The chair supports you only if its internal architecture can redirect the load without allowing a crack, joint, or weak point to fail. This is why design matters. A thin sheet of material may bend easily by itself, but becomes strong when curved, folded, reinforced, or connected to a frame. The strength is not located in one atom or one bond. It emerges from the pattern through which forces travel. Invisible fields and microscopic interactions become engineering. A badly designed chair and a well-designed chair may contain similar materials, yet their structures guide stress differently, producing very different outcomes. Your safety depends on arrangement as much as substance. The chair also contains stored energy. Bend a flexible part, and you change the positions of atoms and molecules slightly, increasing the energy of the structure. Release it, and that energy may return as motion, vibration, and sound. Tighten a screw, and you create tension that helps keep two components pressed together. Compress foam, and its internal framework resists the deformation, then expands when the load is removed. Each response reflects changes in the fields and bonds within the material. The object seems passive, but it continually adjusts to every force placed upon it. Even its stillness is not the absence of activity. It is a balanced state in which competing influences produce no large visible motion. Gravity pulls the chair and your body downward. The floor and the chair's structure provide upward forces. Internal stresses distribute the load. Air pressure acts on every exposed surface. Thermal motion continues within the material. Light and heat arrive and leave. Stillness is simply what this entire system looks like when its large-scale changes cancel. There is a philosophical temptation to hear that matter is made from fields and conclude that the physical world is somehow less real than it appears. But the opposite may be closer to the truth. The chair is real precisely because its pattern is stable enough to resist change, carry weight, and persist through time. Reality does not require objects to be made from tiny hard pieces with no deeper explanation. A wave can be real, a field can be real, a structure can be real. The chair's reality lies not in being an indivisible lump, but in the reliability of its organization. Remove one atom and nothing noticeable happens. Remove many in the wrong place and the chair weakens. Rearrange the same material and it may become a table, a beam, a pile of fragments, or smoke. What matters is not only what is present, but how it is arranged and how that arrangement responds to forces. This is one of the quiet lessons of modern physics. Objects are less like permanent substances and more like maintained patterns. They endure because the laws governing fields allow certain configurations to remain stable for long periods. The chair beneath you may have existed for years, but many of its details are slowly changing. Molecules react with oxygen, moisture enters and leaves, surfaces wear, bonds break and reform, sunlight may alter pigments, metal may corrode, wood may dry or swell. The pattern persists until these small changes eventually become large enough to weaken it. Its identity is continuity, not perfect permanence. And so the next time you sit without thinking, you might notice how much invisible order is required to hold you quietly above the floor. Beneath the fabric and polished surfaces lies no final layer of miniature furniture, only fields arranged into particles, particles organized into atoms, atoms joined into materials, and materials shaped into a structure capable of receiving your weight. The chair feels ordinary because this arrangement is dependable, yet its ordinary presence is the visible result of a deeper world you never directly see. A world in which matter is not separate from fields, stillness is a balance of forces, and support is the temporary stability of an invisible pattern. Quantum tunneling happens inside the devices you use every day. Some of the devices around you work because particles occasionally appear where ordinary physics says they should not be able to go. This effect is called quantum tunneling, and although the name sounds as if a particle is secretly digging a passage through matter, nothing literally burrows through a wall. The idea begins with an energy barrier, a region a particle does not have enough energy to cross in the classical sense. Imagine rolling a ball toward a hill. If the ball is moving too slowly, it climbs part of the way, stops, and rolls back. Classical physics would give the same verdict every time. Without enough energy, the ball cannot reach the other side. A quantum particle is described differently. Its state is not confined to one perfectly sharp location, and the mathematical pattern that describes it can extend slightly into a forbidden region. If the barrier is thin enough, that pattern may reach beyond the far side, creating a real probability that the particle will later be detected there. It has not smashed through the barrier, climbed over it, or borrowed energy in the casual way popular explanations sometimes suggest. Quantum mechanics simply does not assign it the same kind of definite path that a rolling ball would follow. The result is strange, but experimentally undeniable. A particle can cross a barrier even when its measured energy would be insufficient according to classical rules. This probability falls rapidly when the barrier becomes thicker, higher, or more difficult for that kind of particle to penetrate, which is why tunneling matters mainly across extremely small distances. Yet those tiny distances are exactly where modern electronics operate. One of the clearest everyday examples is flash memory, the technology used in solid-state drives, memory cards, USB drives, and the storage systems inside many phones and tablets. A flash memory cell stores information by controlling electrical charge in a carefully isolated region of a transistor. That charge must remain trapped when the device is turned off, sometimes for years, so engineers surround it with insulating material that normally prevents electrons from escaping. To write or erase data, however, the device applies a strong electric field across an extraordinarily thin insulating layer. Under these conditions, electrons can tunnel through the barrier and enter or leave the storage region. The presence or absence of charge changes how the transistor responds when it is read, allowing the circuit to represent digital information. A photograph, a message, or part of an application may therefore remain stored because electrons have been deliberately moved through a barrier they could not cross classically and then held in place after the field is removed. The same process also explains why flash memory wears out. Each program and erase cycle drives charge through a thin insulating layer, and over many repetitions the material can accumulate small defects. Electrons may become trapped in unwanted locations. The distinction between stored states becomes less clear, and the cell eventually becomes less reliable. Storage devices use error correction, spare cells, and wear leveling systems to distribute this damage, but the physical limitation remains. Digital information may feel abstract and permanent, yet it depends on fragile microscopic structures repeatedly managing tunneling events. Another important device is the tunnel diode, a semiconductor component designed so that electrons can tunnel across a very narrow internal barrier. Unlike an ordinary diode, whose current generally rises in a straightforward way as voltage increases, a tunnel diode can pass through a region where increasing the voltage actually reduces the current. This unusual behavior makes it useful in very fast switching, high-frequency circuits, and specialized oscillators. The effect appears because voltage changes the alignment of available electronic states on the two sides of the barrier. At some settings, many states line up and tunneling becomes likely. At others, the alignment becomes worse and the current falls. The device does not operate by forcing electrons harder through a material in the ordinary sense. It works by changing which quantum transitions are available. Resonant tunneling devices take this idea further by placing an extremely thin region between two barriers. At particular energies, the electron's quantum state fits that structure especially well, and transmission rises sharply. Engineers can use this selectivity to build components that respond rapidly and precisely, revealing that quantum design is not merely about making smaller versions of classical machines. Sometimes the useful behavior has no classical counterpart at all. Tunneling is also present in certain kinds of sensors and scientific instruments. A scanning tunneling microscope can map surfaces with astonishing detail by bringing an extremely sharp conductive tip very close to a sample without allowing ordinary physical contact. When a small voltage is applied, electrons tunnel across the tiny gap between the tip and the surface. The tunneling current changes dramatically with distance, so even a minute vertical difference can produce a measurable change. By moving the tip across the surface and adjusting its height to maintain a chosen current, the instrument can reconstruct features on the scale of individual atoms. The resulting image is not a normal photograph of hard little spheres. It is a map related to the electronic structure of the surface and the ease with which electrons can tunnel between the sample and the tip. Still, it allows scientists to study and even manipulate matter with extraordinary precision. In some experiments, individual atoms have been repositioned one by one, not by grabbing them with microscopic fingers, but by carefully controlling their interaction with the probe. Similar tunneling principles appear in superconducting devices. When two superconductors are separated by an extremely thin insulating layer, pairs of electrons can tunnel through it while preserving a shared quantum relationship. This is known as the Josephson effect. Devices built from these junctions can detect incredibly weak magnetic fields and create exceptionally accurate electrical standards. They are used in sensitive medical measurements, advanced laboratory instruments, and some designs for quantum computers. These applications may feel distant from daily life, yet they belong to the same technological world that supports communication, navigation, medical scanning, and precision manufacturing. Tunneling also creates problems as electronic components shrink. In an ideal transistor, an insulating barrier should stop electrical charge when the device is meant to be off. But when that barrier becomes only a few atoms thick, electrons may tunnel through it even without permission. This leakage wastes energy, generates heat, and makes it harder to distinguish the on state from the off state. Engineers cannot eliminate quantum mechanics by building more carefully. The laws become more visible precisely because the structures are so small. This has forced chip designers to develop new insulating materials, three-dimensional transistor shapes, and alternative architectures that maintain control without allowing excessive leakage. The continued progress of electronics has therefore depended on learning when tunneling should be encouraged and when it must be suppressed. In one part of a device, it stores information. In another, it destroys efficiency. The same effect can be a tool or a limit depending on how the surrounding structure is designed. Tunneling should not be confused with particles passing freely through large everyday objects. A human body will not tunnel through a locked door in any meaningful amount of time. Large objects contain enormous numbers of interacting particles, and preserving their complete arrangement through a barrier would require an unimaginably coordinated event, with a probability so close to zero that it can be ignored completely. Quantum mechanics allows outcomes with different probabilities. It does not make every imaginable outcome practically possible. In electronics, tunneling matters because individual electrons face barriers only a few billionths of a meter wide, under carefully controlled conditions designed to make the probability useful. The scale is the entire story. What is absurd for a person can be routine for an electron. This is why the device in your hand can appear ordinary, while depending on behavior that violates ordinary intuition. Each time a memory cell is programmed, each time a specialized sensor measures a tiny current, or each time an advanced circuit exploits a narrow energy window, nature is not momentarily breaking its rules. It is following deeper rules that become hidden when objects are large and distances are familiar. Quantum tunneling does not turn technology into magic. It makes technology possible by revealing that a barrier is not always an absolute boundary. At the smallest scales, a barrier is something that changes probability rather than simply declaring an event impossible. And inside the devices you use every day, engineers have learned to shape those probabilities so carefully that something once regarded as one of the strangest predictions in physics can store your memories, control electrical signals, and quietly keep the modern world running. The sun shines because particles cheat through barriers. The sunlight warming your face exists because the center of the sun accomplishes something that ordinary physics alone would forbid. Deep inside that enormous sphere of plasma, hydrogen nuclei are packed under crushing pressure and heated to temperatures of millions of degrees, moving rapidly through a dense environment where collisions happen constantly. You might expect such conditions to make fusion easy, but even the sun's core is not hot enough for most hydrogen nuclei to overcome their electrical repulsion in the classical way. Each nucleus carries a positive charge, and as two of them approach, they push each other apart more strongly. To fuse, they must come extremely close enough for the powerful but very short-range nuclear force to take control and bind them together. The difficulty is that the electrical barrier rises before they reach that distance. If the nuclei behaved only like tiny classical balls, most of them would approach, slow down, and separate again, leaving the sun far dimmer than the star you see. But atomic nuclei are quantum objects, and their behavior cannot be reduced to definite particles following perfectly fixed paths. Their quantum states possess a small spread, and when two nuclei come near one another, there is a tiny probability that their states will extend through the repulsive barrier far enough for the nuclei to reach the region where fusion can occur. This is quantum tunneling at a cosmic scale. Not the entire sun passing through anything, but individual nuclei crossing a barrier that their ordinary thermal energy would rarely be sufficient to climb. The word cheat is useful only as a metaphor. The particles do not break the laws of nature, steal extra energy, or briefly ignore electrical repulsion. They follow quantum laws in which a barrier lowers the probability of crossing rather than always reducing it to absolute zero. For any single encounter, fusion is highly unlikely. A proton in the sun may experience enormous numbers of near collisions and still wait billions of years before participating in the specific reaction that begins the main fusion chain. This slowness is essential. If hydrogen fused too easily, the sun would consume its fuel rapidly and release energy at a catastrophic rate. Instead, the first step in the dominant proton-proton chain is remarkably rare. Two protons come close through tunneling, but one of them must also transform into a neutron through the weak nuclear interaction. The result is a deuterium nucleus, made of one proton and one neutron, along with other tiny particles that carry away energy and conserve the required physical quantities. This transformation is slow because the weak interaction is genuinely weak, and that delay acts like a cosmic regulator. The sun is bright, not because fusion is effortless, but because an almost unimaginable number of particles are present in its core. Even an extremely improbable event becomes frequent when it is attempted throughout a region containing vast amounts of hydrogen, second after second, across billions of years. Once deuterium has formed, it can combine with another proton more readily, producing a light form of helium and releasing energy. Later reactions bring these nuclei together to create ordinary helium, and over the full chain, a small amount of mass is converted into energy. The final helium nucleus has slightly less mass than the hydrogen nuclei from which it was assembled. That difference does not vanish. It emerges as energy carried by moving particles and radiation, heating the solar interior and ultimately helping sustain the sun's outward pressure. The fusion energy is not created from nothing, nor is it released because atoms simply collide hard enough to explode. It comes from the change in nuclear binding. The final arrangement is more tightly bound, and the system releases the difference as energy. Yet the light produced in the core does not travel directly to Earth. The sun's interior is so dense that high-energy photons are repeatedly absorbed and re-emitted, scattered, and transformed. A photon may move only a short distance before interacting again, and the energy follows an indirect journey outward that can take an extremely long time. During that journey, the original high-energy radiation is redistributed into many lower-energy photons. The visible light leaving the solar surface is therefore not a collection of untouched photons born during ancient fusion events and flying straight outward. It is the final expression of energy that has been exchanged throughout the solar plasma countless times. Once that energy reaches the visible surface, known as the photosphere, photons can escape much more freely. They cross space in about 8 minutes before reaching Earth, where some are absorbed by land and ocean, some drive weather and climate, some support photosynthesis, and some enter your eyes. The brightness above you is thus separated from its origin by several distinct processes. Quantum tunneling allows rare nuclear encounters. The weak interaction controls the slow first step. Nuclear binding releases energy. The solar interior transports and reshapes that energy, and the surface finally sends it into space. Gravity holds the entire system together. The sun's enormous mass compresses its core, raising the density and temperature enough for tunneling-assisted fusion to occur at the rate required. Fusion then provides energy that heats the plasma and creates pressure directed outward. For most of the sun's stable life, these opposing tendencies remain in balance. Gravity pulls inward, while hot matter and radiation resist collapse. The sun is not a stationary fire suspended in space. It is a self-regulating star whose structure continually adjusts to maintain equilibrium. If the core were compressed slightly, it would heat up and fusion would accelerate, increasing outward pressure. If the core expanded and cooled, fusion would slow, allowing gravity to compress it again. This feedback helps keep the Sun stable over immense spans of time. It also explains why comparing the Sun to ordinary burning is misleading. Fire on Earth is a chemical reaction involving electrons and molecular bonds, and it requires available fuel and oxidizing material. The Sun is not burning oxygen. Its energy comes from nuclear reactions occurring under conditions that do not exist in an ordinary flame. The temperatures in the core strip electrons from atoms, leaving a plasma of charged particles and radiation. What shines in the sky is not a giant campfire, but a gravitationally confined nuclear system whose central reactions depend on quantum probability. The process is still selective. Faster-moving nuclei have a better chance of approaching closely, but tunneling probability also matters, so fusion is concentrated within a particular range of energies. The most energetic particles are rare, while slower particles are common, but less likely to penetrate the barrier. The combination creates a narrow region where useful reactions occur most effectively. This helps scientists understand how fusion rates respond to changes in core temperature and why different stars follow different nuclear pathways. In stars more massive than the Sun, hotter cores make other fusion cycles more important. In smaller and cooler stars, reactions proceed more slowly, allowing them to remain active for far longer. The life of a star is therefore shaped not only by how much fuel it contains, but by the probabilities governing how nuclei meet. This same knowledge guides attempts to create controlled fusion on Earth. Scientists heat hydrogen isotopes to extreme temperatures and confine the plasma using magnetic fields or powerful lasers, trying to produce enough successful fusion reactions to release useful energy. Tunneling helps make fusion possible, but it does not make engineering easy. The plasma must be hot and dense enough, confined long enough, and protected from impurities and instabilities. Nature has the advantage of a star's enormous gravity and size. Laboratories must recreate the relevant conditions with machines. The challenge itself reveals how delicately the Sun works. Its light may appear effortless, arriving every morning without sound, yet its production depends on rare events repeated on a scale beyond ordinary imagination. And this changes the meaning of sunlight in a quiet way. The warmth on your skin began where positively charged nuclei should have repelled one another and separated. Most did, a tiny fraction did not. Quantum mechanics allowed enough of them to reach the hidden range where the nuclear force could reshape them, and gravity maintained the conditions for this to continue slowly across billions of years. The Sun shines not because every barrier is easily defeated, but because nature sometimes replaces the word impossible with a very small probability, and then gives that probability an entire star in which to keep trying. Your computer chip is built on quantum rules. The computer chip inside your device does not calculate by thinking. It calculates by controlling whether unimaginably small regions of material allow electrical charge to move or prevent it from moving. And the reason this control is possible begins with quantum physics. At the heart of most modern chips is silicon, an element that is neither a strong electrical conductor like copper nor a complete insulator like glass. Silicon belongs to a useful middle category known as a semiconductor. Its special behavior comes from the way electrons are allowed to exist inside a solid. In an isolated atom, electrons can occupy particular energy states. But when enormous numbers of atoms are brought together in a crystal, their individual states combine into broad ranges called energy bands. Some bands are mostly filled, while others contain states into which electrons can move and carry current. Between them lies an energy gap where no stable electron states are available. In a good conductor, electrons can move into nearby available states with little difficulty. In a strong insulator, the gap is too large for ordinary conditions to move enough electrons into conducting states. Silicon sits between these extremes. Its gap is large enough to restrict current when required, but small enough that engineers can change its behavior using heat, light, electrical fields, and carefully chosen impurities. This controllability is what makes silicon more valuable to computing than a material that simply conducts all the time. A chip needs billions of regions that can be switched between allowing current and blocking it. It needs matter whose electrical behavior can be instructed. Pure silicon begins as a crystal in which each atom shares electrons with neighboring atoms through chemical bonds. At low temperatures, many of these electrons remain tied into the bonding structure and cannot move freely through the crystal. Engineers alter this by adding tiny amounts of other elements in a process called doping. The name may sound crude, but the process is extremely precise. Add atoms with one more outer electron than silicon, and the material gains electrons that can move relatively easily. Add atoms with one fewer, and the crystal develops vacancies often called holes. A hole is not a physical bubble moving through the material. It is an unoccupied electronic state that behaves as if a positive charge were traveling in the opposite direction as neighboring electrons repeatedly fill the vacancy. By placing differently doped regions beside one another, engineers create boundaries that guide, restrict, and redirect current. These boundaries form the basis of diodes and transistors, the microscopic components from which digital machines are built. The most important transistor in modern computing is commonly the field effect transistor. It contains regions through which charge could flow, but the path between them can be opened or closed by a nearby control terminal called a gate. The gate does not need to push individual electrons along like a mechanical piston. It creates an electric field that changes the energy landscape inside the semiconductor. Under 1 gate voltage, the available charge carriers are kept away from the path, leaving the transistor effectively off. Under another voltage, enough carriers gather to form a conducting channel, and current can flow. The switch contains no moving lever, yet it can change state billions of times per second, because an electrical field can reorganize the behavior of electrons far faster than a mechanical device could move. This is where quantum rules become computation. The chip interprets different voltage ranges as logical states such as 0 and 1. A single transistor is not intelligent and does not know what a number means. But transistors can be connected into logic gates that perform simple operations, combining inputs, reversing them, storing a temporary state, or deciding whether a signal should continue. Connect enough logic gates and they can add numbers, compare values, move information, decode instructions, and control memory. The image on your screen, the sound from a speaker, and the motion of a game character eventually depend on vast networks of these switches changing in carefully timed patterns. The meaning appears at the level of the system, while the material beneath it remains occupied with a simpler question: is charge allowed to move here now or not? The extraordinary power of a modern processor comes partly from scale. A chip may contain billions of transistors arranged across a piece of silicon small enough to rest on a fingertip. Each transistor must be patterned with extreme accuracy using photolithography, a manufacturing process that uses light, masks, chemical reactions, and repeated layers to define microscopic structures. The process does not simply carve a tiny circuit into a block. Manufacturers build the chip through many cycles of depositing materials, exposing patterns, removing selected regions, introducing dopants, creating insulators, and adding metal connections. Some advanced chips contain dozens of interconnected layers, with transistors near the silicon surface and intricate networks of wiring above them. Those wires distribute power, carry signals, and connect parts of the processor that may be performing very different tasks. A chip that looks flat from the outside is really a three-dimensional city of electrical pathways, switches, barriers, and junctions. Yet making transistors smaller creates difficulties because electrons do not behave like perfectly obedient beads. At tiny scales, electrical fields from one region can influence neighboring regions. Small variations in the placement of atoms can affect performance. Heat generated by switching becomes difficult to remove. Signals can interfere, and the distinction between a clear off state and a clear on state becomes harder to preserve. Engineers respond not only by shrinking the same old shape, but by changing the architecture. Some transistors wrap the gate around raised channels so the electrical field can control them from several sides. Newer designs may surround the conducting channel even more completely, improving control while reducing unwanted current. This reveals an important truth about technological progress. Smaller does not automatically mean better. A useful transistor must switch reliably, use little energy, operate quickly, survive manufacturing variation, and connect efficiently with billions of others. Every improvement is a negotiation among quantum behavior, materials science, heat, geometry, and cost. Even the clock speed printed on a processor tells only part of the story. A faster rhythm does not guarantee greater performance if the chip wastes time moving data or waiting for memory. Modern processors therefore contain specialized regions. Some handle general instructions, some perform graphics calculations, some predict likely future instructions, and others accelerate tasks such as machine learning. Their designs differ, but each is still constructed from electronic components whose behavior depends on energy bands, charge carriers, and electric fields. Software may appear distant from physics, yet every instruction eventually becomes a pattern of voltages applied to real material. A command to open a photograph is translated through many layers, from an operating system and program code into machine instructions, then into switching events inside physical circuits. The abstraction feels weightless, but its execution is not. It requires energy, produces heat, occupies time, and depends on the quantum properties of silicon being stable enough to distinguish one state from another. This is why a computer can crash when hardware overheats, why radiation from space can occasionally disturb stored information, and why manufacturing defects can ruin a processor too small for the eye to inspect directly. Computation is never separate from matter. It is matter arranged so precisely that physical changes can represent symbols. The chip does not contain miniature numbers flowing through microscopic pipes. It contains changing distributions of charge that humans have chosen to interpret as numbers, letters, images, and instructions. The same electron movement might represent part of a song in one moment and part of a financial calculation in another. Meaning is not built into silicon. It is created by the organized relationship between hardware, code, and the people using it. And perhaps this is the most remarkable thing hidden inside your computer. Quantum physics does not merely explain why the chip functions. It allows a material with carefully controlled electronic possibilities to become a machine for handling ideas. Beneath every document, simulation, message, and digital memory lies a silent crystal in which electric fields repeatedly reshape where electrons are permitted to move. The device seems to operate in a world of information, but its information survives only because the quantum structure of matter can be trained to say no, then yes, then no again with extraordinary speed and reliability. Why colors do not live inside objects. A red apple is not carrying redness inside its skin, waiting for your eyes to collect it. What you call color is an experience assembled only when light, material, eye, and brain meet in the right way. In darkness, the apple has no visible red at all, and even under light, it does not send out a label saying red. Its surface contains pigments and microscopic structures that absorb some wavelengths of incoming light more strongly than others and return a particular mixture toward your eyes. That reflected mixture is only the beginning. Light itself does not contain color in the form you experience it. It contains different wavelengths and combinations of wavelengths, physical differences that can be measured, but the sensation of crimson, turquoise, gold, or violet appears only after a nervous system interprets those differences. This is why color cannot be placed entirely inside the object or entirely inside the light. It is a relationship. Change the illumination, and the object's appearance may shift, even though the object itself has not been repainted. A white shirt under warm indoor lighting may send a very different spectrum into your eyes than it does beneath a blue sky. Yet your brain often continues to judge it as white. This ability is called color constancy, and it shows that vision is not a passive reading of wavelengths. Your brain estimates the nature of the surrounding light and partially corrects for it, trying to preserve the likely identity of surfaces as conditions change. The correction is useful because sunlight varies throughout the day. Shadows alter the light reaching objects, and artificial lamps have very different spectral mixtures. Without this adjustment, familiar objects would seem to change color constantly, but the process is not perfect. Which is why two people can disagree about the color of the same photograph when the lighting context is ambiguous. Their brains may make different assumptions about what kind of illumination should be mentally removed. The disagreement does not mean either person is lying. It reveals that color perception includes an unconscious act of interpretation. Your eyes begin this interpretation with several kinds of light-sensitive cells. Rod cells are highly sensitive in dim conditions, but contribute little to ordinary color vision, which is why a moonlit landscape often seems drained of color. Cone cells work best in brighter light and come in types with overlapping sensitivities to different regions of the visible spectrum. It is misleading to imagine them as simple red, green, and blue detectors, because each type responds to a broad range of wavelengths. Your brain compares their relative activity. A single cone cannot identify the wavelength of the light that stimulated it, because a weak response could come from dim light near its preferred range or brighter light farther away from it. Color information emerges from the pattern across many cones, not from one receptor announcing a color by itself. The brain then reorganizes these signals into opposing channels, roughly comparing reddish against greenish tendencies and bluish against yellowish tendencies, along with a separate sense of brightness. This opponent structure helps explain why you do not normally see a color that is simultaneously reddish and greenish in the same place, and why staring at one strong color can produce an afterimage in its opponent. Look at a bright red patch for a while, then shift your eyes to a pale wall, and you may see a greenish ghost. The wall has not changed. Your visual system has adapted to the original stimulation, temporarily altering the balance of its response. The afterimage is a quiet demonstration that color is being produced within an active biological system rather than simply copied from the world. The same physical object can also look different to different observers. People vary in the pigments inside their cones, in the number and distribution of those cells, in the lenses of their eyes, and in how their brains process visual signals. Some forms of color vision deficiency occur when one cone type is absent or responds differently, making certain distinctions harder to perceive. Other species inhabit sensory worlds unlike yours. Many birds can detect ultraviolet wavelengths that human eyes cannot see. Some animals have fewer kinds of color receptors, while others possess more. A flower that appears yellow to you may contain ultraviolet patterns guiding an insect toward nectar. Patterns that exist physically as differences in reflectance but never become part of ordinary human experience. There is therefore no single complete visual color map possessed by every living observer. The material world contains patterns of light interaction, while each nervous system samples and translates only part of them. Even two physically different mixtures of light can sometimes look identical to you. These matches are called metamers. A screen can create the impression of yellow by combining suitable red and green light, even though the spectrum reaching your eyes is not the same as the spectrum reflected by a yellow flower. Your cone responses happen to be similar enough that the brain assigns both signals a comparable color experience. This is one reason cameras and displays can reproduce convincing scenes using only a limited set of channels. They do not need to recreate every wavelength exactly. They need to stimulate human vision in a sufficiently similar pattern. But a match that works for one observer or one lighting condition may fail for another. Two fabrics that look identical in a shop can appear different outdoors because their reflectance spectra are not truly the same. The original lamp happened to make their responses look alike, while daylight exposes the difference. Color is also shaped by context. A grey square can look lighter against a dark background and darker against a bright one. Identical colors may appear different when surrounded by contrasting hues. Your brain evaluates local relationships, edges, shadows, and probable lighting rather than treating each point independently. This allows it to infer surfaces more reliably in complex scenes, but it also creates illusions. A shadow does not merely reduce brightness. The brain may reinterpret the entire region as being under different illumination and compensate for it. That compensation can make two identical patches appear dramatically unequal. In ordinary life, this system helps you recognize fruit in shade, read a face near a window, or identify clothing under changing lamps. In a carefully designed image, the same shortcuts can be turned against you. The fact that color depends on interpretation does not make it imaginary. Pain is produced by a nervous system, yet an injury is still real. Music emerges when pressure variations are interpreted by an auditory system, yet the sound of an orchestra is not meaningless. In the same way, color is a real perceptual phenomenon grounded in measurable light, material properties, receptors, and neural processing. What is false is only the instinct that redness exists inside an apple exactly as mass or chemical composition does. The apple possesses a reflectance pattern, its pigments possess molecular structures, and the surrounding light possesses a spectrum. Redness is what your visual system makes from that encounter. Remove the light and the visible color disappears. Change the observer and the experience may change. Alter the surroundings and the same signal may be judged differently. Yet the world does not become arbitrary, because the process is constrained by physics and biology. Certain materials consistently absorb and reflect particular wavelengths. Cone cells respond in reproducible ways, and neural circuits compare those responses according to dependable patterns. Color is not a property floating freely without cause. It is an emergent result that belongs to the whole interaction. This may change the way you look at ordinary things. The green of a leaf is not stored like paint inside the leaf, but arises because its pigments interact with available light, and your visual system interprets what returns. The blue of the sky is not a blue substance filling the atmosphere, but the perceptual result of sunlight being scattered differently across wavelengths. The warmth of a sunset does not reside inside the horizon. It appears when light has crossed a long path through the atmosphere, lost more of some wavelengths than others, and reached a brain capable of turning the remainder into a scene of orange and red. Everywhere you look, color seems attached to objects because your mind binds the experience to its most likely source. That binding is so fast and convincing that you rarely notice the construction. You simply see a red cup, a green tree, a blue coat. But beneath that simplicity lies a constant act of comparison, correction, and interpretation. The world gives you light shaped by matter. Your eyes measure only a fragment of it. Your brain transforms those measurements into a stable visual language. Color does not live inside objects, yet it is not detached from them either. It lives in the meeting place where the physical world becomes experience, reminding you that seeing is never merely receiving reality. It is the quiet work of turning invisible differences into a world that feels vividly present. The quantum secret inside every battery. Every battery is a small chemical landscape designed to keep electrons on one side until you give them a path to escape. The energy inside it is not stored as a pool of electricity waiting to pour out, and the battery does not manufacture electrons from nothing when you press a button. Its secret lies in the different quantum arrangements that electrons prefer inside different materials. A battery contains two electrodes made from substances with unequal chemical tendencies, separated by an electrolyte that allows certain charged atoms or molecules to move while preventing the electrodes from simply reacting with each other all at once. One electrode holds electrons in states from which they can be released relatively easily, while the other offers lower energy arrangements that those electrons can occupy. This difference creates voltage, not a physical pressure trapped inside the casing, but an electrical potential produced by the contrasting energies and chemical environments on the two sides. When the battery is disconnected, the reactions quickly reach a point where further charge separation becomes difficult. Electrons gather where they are produced, making that region increasingly negative, while the other side lacks electrons and becomes relatively positive. This electrical imbalance resists additional reaction, so the process largely pauses. Connect the terminals with a conducting circuit, however, and the stored imbalance gains a route through which it can relax. Electrons move through the external wire toward the electrode, where lower energy states are available, and their directed flow can power a lamp, motor, sensor, or processor along the way. Inside the battery, ions move through the electrolyte to maintain electrical balance. Without this internal ionic motion, charge would accumulate rapidly and stop the current. The complete circuit therefore contains two linked journeys. Electrons move through the device outside the battery, while ions rearrange inside it. Neither journey alone is enough. The chemistry pushes the process forward, the circuit guides the electrons, and the electrolyte prevents the system from locking itself through charge buildup. Quantum physics enters because chemical reactions are ultimately rearrangements of electrons among allowed states. Atoms do not bind in arbitrary ways, and electrons cannot settle at any energy they please. Their permitted arrangements depend on the identities of the atoms, the structure of the electrode, and the surrounding chemical environment. During discharge, atoms at one electrode may lose electrons and become ions, while material at the other electrode accepts electrons and changes composition. The electrons tend to move through the outer circuit because the available final arrangement of the entire system has lower energy than the initial one. The battery's useful energy comes from this difference between chemical configurations. It is released gradually as the materials transform, not because an electron carries a private supply of energy like a tiny delivery vehicle. The electric field established throughout the circuit transfers energy to components, while individual electrons in a metal usually drift much more slowly than the signal and energy spread through the circuit. This is why a lamp can respond almost immediately. Even though no particular electron needs to travel from the battery all the way to the bulb at extraordinary speed. The electrons were already present throughout the wire. Connecting the battery reorganizes the electric field, encouraging charges across the circuit to begin a coordinated drift. Different battery chemistries create this energy difference in different ways. In a common alkaline battery, zinc at one electrode is gradually oxidized, meaning it loses electrons, while manganese dioxide at the other side participates in reactions that accept those electrons. The chemistry is arranged so the electrons cannot take a direct internal shortcut. They must travel through the external device if they are to reach the other electrode. In a lithium-ion battery, the process is more reversible. Lithium ions move between host materials whose atomic structures contain spaces capable of receiving them. During discharge, lithium atoms at the negative electrode effectively separate into lithium ions and electrons. The ions travel through the electrolyte, while the electrons move through the external circuit. At the positive electrode, both are incorporated into a new arrangement. Charging applies energy from an outside source and drives the system in the opposite direction, pushing lithium ions back toward the negative electrode and restoring a higher energy chemical configuration. This does not reset the battery with perfect precision. Each cycle can produce tiny unwanted changes. Electrolyte molecules may break down, protective layers may grow, electrode particles may crack, and some lithium may become trapped where it can no longer participate efficiently. Over time, fewer active ions remain available, internal resistance rises, and the battery stores less energy. The gradual decline you notice after years of charging a phone is the macroscopic result of microscopic structures failing to return completely to their original state. Temperature strongly affects these processes. In cold conditions, chemical reactions slow, ions move less readily through the electrolyte, and the battery may struggle to deliver high current even though much of its chemical energy remains. Warm it gently and some apparent capacity may return. Excessive heat causes the opposite danger. Reactions accelerate, unwanted chemical breakdown becomes more likely, and the battery can age rapidly. In severe cases, heat triggers further reactions that release still more heat, creating a self-reinforcing process known as thermal runaway. This is why lithium-ion batteries require separators, electronic monitoring, pressure relief, temperature controls, and charging systems that carefully limit current and voltage. The separator is especially important. It keeps the two electrodes physically apart while allowing ions to pass through microscopic pores. If it tears, melts, or is pierced, the electrodes may form an internal short circuit, allowing electrons to bypass the intended external path. Energy is then released rapidly inside the cell as heat rather than being delivered safely through a device. A battery's usefulness depends on preventing its chemistry from reaching equilibrium too quickly. It is, in a sense, a controlled delay. Two materials are allowed to exchange charge only through a route designed to perform work. The amount of voltage depends on the difference in chemical potential between the electrodes, while the available current depends on reaction rates, internal resistance, temperature, surface area, and design. This explains why two batteries with the same voltage can behave very differently. A small coin cell may power a watch for years, but fail to start a motor because it cannot safely supply a large current. A vehicle battery can release an intense burst because it has large electrodes and chemistry suited to rapid delivery. Capacity and power are related but not identical. Capacity describes how much charge can be transferred before the useful chemical difference is exhausted, while power describes how quickly energy can be delivered. Increasing one may compromise the other, and every practical battery balances weight, size, safety, lifespan, charging speed, cost, and energy storage. Even the percentage displayed on your phone is not a direct measurement of a visible fuel level. The device estimates remaining charge by monitoring voltage, current, temperature, past behavior, and mathematical models of how the cell responds. Because battery voltage changes in complicated ways during use, the percentage is an informed prediction rather than a perfect count of electrons. This is why the indicator can occasionally fall unexpectedly, remain at one value for a long time, or become more accurate after the device learns the battery's aging behavior. A fully charged battery does not contain more total electrons than a discharged one in any important overall sense. The difference is where charge resides and how the atoms and ions are arranged. Charging does not stuff the cell with a new population of electrons. It uses external energy to push its chemistry back into a less relaxed configuration, restoring the separation from which useful work can later be extracted. That is why a battery can be thought of as stored possibility rather than stored electricity. Its materials have been prepared in an arrangement that is not yet at equilibrium, and the circuit gives them a controlled way to move toward a more stable state. The quantum secret is therefore not one exotic event hidden inside the casing. It is the entire hierarchy of allowed electron states, chemical bonds, ion motion, and energy differences that makes the reaction directional and useful. When a battery powers your phone, the device is not drawing from a miniature reservoir of lightning. It is guiding matter through a sequence of quieter transformations, allowing electrons to leave one chemical environment, travel through a circuit where their motion becomes useful, and settle into another arrangement that nature prefers. What looks from the outside like a percentage slowly falling is, inside, a vast number of atoms changing partners, ions crossing a separator, and electrons descending through an energy landscape shaped by quantum rules. The battery eventually becomes empty, not because its electrons are gone, but because the chemical difference that once persuaded them to move has largely disappeared. The materials have approached a state with less remaining capacity to perform work. Magnets work because electrons have a hidden spin. A magnet can pull a piece of iron across a table without touching it, yet the source of that invisible influence is not a hidden current circling inside the metal like water in a pipe. It begins with a quantum property of electrons called spin. The name is misleading, because an electron is not a tiny ball physically rotating around its own surface. If it were, the simple picture would fail almost immediately. Spin is an intrinsic form of angular momentum, a built-in quantum characteristic that electrons possess in the same fundamental way they possess electric charge. You cannot peel it away, slow it to a stop, or watch one side of the electron rotate into view. What spin does provide is a magnetic moment, which means each electron behaves in some respects like an extremely small magnet with an orientation. In most ordinary materials, These microscopic magnetic contributions do not combine into a large visible effect. Electrons often occur in pairs whose spins point in opposite quantum directions, causing their magnetic moments to cancel. Even when unpaired electrons are present, thermal motion and the local structure of the material may leave their orientations disordered. So one tiny magnetic contribution points one way, while another points somewhere else. The object then produces little or no permanent external field. Iron, cobalt, nickel, and certain alloys behave differently because their atomic structure allows a special quantum interaction between neighboring electrons. This is called the exchange interaction, and it does not arise from miniature magnets simply pulling themselves into line like compass needles. It comes from the combined quantum state of electrons, their spin, their electrical repulsion, and the rule that identical electrons cannot all occupy the same state. Under suitable conditions, the material reaches a lower energy arrangement when many neighboring spins align in a coordinated direction. That alignment creates regions called magnetic domains. Inside a single domain, enormous numbers of atomic magnetic moments point largely together, producing a strong local magnetization. But a fresh piece of iron may still appear unmagnetized because its domains point in different directions. One domain's field is balanced by another, and the overall object hides its internal order. Bring a strong magnet close and the balance changes. Domains already oriented favorably can grow, while others shrink or rotate. Boundaries between them move through the material, allowing more of the internal magnetization to point in the same general direction. In soft iron, much of this alignment disappears after the external magnet is removed, which makes the material useful in electromagnets and transformer cores. In harder magnetic materials, defects in crystal structure make domain boundaries more difficult to move. The alignment can remain trapped, leaving the object permanently magnetized. This is why making a strong permanent magnet is not just a matter of choosing a metal with magnetic atoms. The internal structure must help preserve the chosen arrangement. Modern magnets may use alloys containing elements such as neodymium, iron, and boron because their crystal structure creates strong directional preferences for magnetization. This preference, known as magnetic anisotropy, makes certain spin orientations more stable than others and helps the magnet resist being casually demagnetized. The familiar north and south poles do not belong to two separate substances stored at opposite ends. They arise from the collective field produced by the aligned magnetic moments throughout the material. Break a bar magnet in half, and you do not isolate a north pole from a south pole. Each piece becomes a smaller magnet with both poles because the internal alignment still creates a complete field pattern. The field lines commonly drawn around a magnet are not physical threads floating in the air. They are a visual way of showing the direction and strength of the magnetic field from place to place. A compass needle turns because the field exerts a torque on its own magnetic moment, encouraging it to align with the surrounding field. Iron is attracted because the external magnet reorganizes magnetic regions inside the iron, creating a nearby orientation that leads to a net pull toward the stronger part of the field. This is why a magnet can attract an unmagnetized paperclip. The paperclip does not need to begin as a permanent magnet. Its internal domains respond to the field and temporarily form a pattern that favors attraction. Not every material responds this way. Paramagnetic substances contain magnetic moments that tend to align weakly with an applied field, but thermal disorder quickly breaks that alignment when the field is removed. Diamagnetic materials respond in the opposite direction. An applied magnetic field slightly alters the motion and quantum states of their electrons, creating a weak magnetic response that opposes the field. Diamagnetism exists in all matter, though it is usually hidden by stronger effects. Under extremely powerful fields, even water, graphite, and living tissue can experience measurable magnetic forces. This does not mean ordinary household magnets can lift a person or pull water from a glass. The effect is far too weak under normal conditions. It does show that magnetism is not limited to objects we casually label magnetic. Different materials answer a magnetic field in different ways because their electrons are arranged differently. Temperature can also destroy the order inside a permanent magnet. As a magnetic material is heated, atomic vibrations and thermal disorder become more intense. Above a characteristic temperature called the Curie temperature, the coordinated spin alignment responsible for ferromagnetism can no longer remain stable. The material does not lose the electron spin itself. Electrons still possess their intrinsic magnetic moments. What disappears is the large-scale cooperation among them. The magnet becomes more like a crowd whose members still have individual directions but can no longer maintain a shared formation. Cooling the material again restores the possibility of magnetic order, but it may not automatically restore the original domain pattern. This is why excessive heat can permanently weaken a magnet unless it is magnetized again. Mechanical shocks, opposing magnetic fields, and corrosion can also disturb the structure and reduce performance. The strength of a magnet is therefore not an eternal substance sealed inside it. It is a maintained arrangement vulnerable to changes in temperature, chemistry, and crystal structure. Electromagnets reveal another path to magnetism. When electric current flows through a coil, moving charge creates a magnetic field around it. Place an iron core inside the coil, and the field encourages the core's domains to align, greatly strengthening the result. Switch off the current, and much of the magnetism may fade. Electric motors, loudspeakers, relays, generators, medical scanners, and countless industrial machines rely on this close relationship between electricity and magnetism. Yet the permanent magnet on a refrigerator and the controlled field in a motor ultimately connect to the same quantum foundation. Electrons carry charge, possess spin, and occupy states whose organization determines how matter responds. There is also orbital magnetism, associated with the quantum motion of electrons within atoms. So spin is not the only source of magnetic behavior. In many important magnetic materials, however, electron spin provides the dominant contribution, shaped by the surrounding atomic environment and exchange interactions. The full story is therefore not that magnets work because every electron points in one direction, nor that spin alone guarantees magnetism. Most materials contain spinning electrons and are not permanent magnets. Strong magnetism appears only when quantum rules, unpaired electrons, crystal structure, and collective alignment cooperate. The extraordinary part is that a property with no exact everyday equivalent can become large enough to hold a note against a refrigerator, turn a motor, store information, and guide a compass across the Earth. You never see the individual spins, and no microscope shows them as tiny rotating tops. Yet their collective order becomes a force your hand can feel. A magnet is not mysterious because it violates nature's rules. It is mysterious because invisible quantum identities, repeated across an enormous number of electrons, can organize themselves so completely that the hidden architecture of matter reaches outward and moves the visible world. Why wires carry electricity without electrons racing like tiny bullets? The lamp turns on almost the instant you flip the switch, yet the electrons inside the wire are not racing from the switch to the bulb like tiny bullets fired through a metal tunnel. That familiar picture feels natural because electricity seems to travel quickly, but it confuses the motion of individual charge carriers with the movement of electrical energy and information through a circuit. A metal wire already contains an immense population of mobile electrons before the circuit is connected. These electrons are not waiting motionless in a line. Even without an applied voltage, they occupy quantum states throughout the metal and possess rapid microscopic motion in many directions, constantly interacting with the ordered lattice of positively charged atomic cores, impurities, vibrations, and defects. Because these motions are distributed in every direction, they produce no sustained current. There is activity, but no net flow. When a voltage is applied, an electric field becomes established along the circuit and slightly biases this restless electron population, giving it a small average drift in one direction. That average drift is surprisingly slow, often far slower than walking speed and, under many ordinary conditions, potentially only fractions of a millimeter per second. The exact value depends on the wire, current, and thickness. But the important point remains. The electrons do not need to cross the entire circuit quickly for the device to respond quickly. The wire behaves more like a long system already filled with movable charge. Push the electrical conditions at one end, and electrons throughout the circuit begin adjusting almost together as the electromagnetic influence spreads through and around the conductor. A useful comparison is a pipe completely filled with water. If you push water into one end, water may emerge from the other end quickly, even though the individual molecule entering the pipe has not traveled the entire length. But even this analogy is incomplete, because electrical energy is not carried only inside the metal by electrons passing it from hand to hand. The electromagnetic field surrounding the conductors plays a central role. The battery or power source establishes a field configuration across the circuit, and this field directs energy through the space around the wires toward the component that uses it. The electrons inside the metal respond to that field, creating the current and guiding the field's pattern. While the energy flow can be described as moving through the electromagnetic environment around the conductors. This is why circuit layout matters, why nearby wires can influence one another, and why signals behave differently at high frequencies. The metal is not merely a hollow channel containing a stream of charged pellets. It is part of a larger electromagnetic structure. Quantum physics explains why metals can support current at all. When many metal atoms form a solid, their electronic states combine into bands, and in a conductor, there are available states close enough in energy that electrons can change their collective motion when an electric field is applied. Yet they do not accelerate forever. As electrons respond to the field, their ordered momentum is repeatedly disrupted by interactions with the vibrating atomic lattice, structural defects, and impurities. These disturbances convert some of the organized electrical energy into disordered motion, which appears as heat. This is electrical resistance. A warmer wire usually has stronger atomic vibrations, creating more opportunities to scatter the electrons and making current harder to sustain. Different metals resist current by different amounts because their crystal structures and electronic states affect how easily the carriers move. Copper is widely used not because its electrons travel like perfectly free projectiles, but because its quantum and material structure allows current to flow with relatively low resistance while remaining practical and durable. In a direct current circuit, the average drift maintains one overall direction. In the alternating current supplied to homes, however, the electric field reverses repeatedly, so the electrons mostly shift back and forth over tiny distances, rather than traveling from a power station into your appliance. The energy still reaches the appliance because the changing electromagnetic field propagates through the connected network. An electron vibrating inside a local section of wire can participate in delivering power without ever making a long journey through the electrical grid. This overturns the common image of electricity as a substance consumed by a device. A lamp does not catch electrons, use them up, and leave the wire empty. Charge continues around the complete circuit, while the lamp transforms transferred electrical energy into light and heat. The number of electrons entering a functioning component is essentially balanced by the number leaving it, even though the energy associated with the circuit decreases across the component. The charges act more like participants in an organized response than disposable packets of fuel. This also explains why a broken circuit stops working. If the path is interrupted, charge quickly accumulates at the exposed ends, creating an opposing field that prevents a steady current from continuing. The electrons do not fail because they cannot leap across the gap quickly enough. The entire electrical arrangement changes because there is no continuous conducting route through which the field can maintain the required charge motion. In very small gaps or under sufficiently high voltage, the surrounding material may become ionized and form a spark, creating a temporary conducting path. The sudden flash shows that current depends not only on the presence of electrons, but on whether the surrounding medium offers accessible ways for charge to move. Circuit response also is not literally instantaneous. Changes in the electromagnetic field travel at a large fraction of the speed of light, with the exact speed influenced by the wire and its insulation. In a short household circuit, That delay is far too small for your sensors to notice. In long communication cables and high-speed computer systems, however, the delay becomes important. Engineers must treat wires as transmission lines, carefully managing reflections, timing, impedance, and interference. A voltage pulse can bounce from a poorly matched connection, much as a wave reflects from a boundary, corrupting the information it carries. At high speeds, even a short copper trace on a circuit board cannot be treated as a simple ideal line. Its geometry becomes part of the signal. The modern world therefore depends on understanding electricity, not as bullets rushing through tubes, but as coordinated charge behavior shaped by fields, materials, and wave propagation. When you press a switch, the nearest electrons move only slightly, and electrons farther along respond to the changing field in their own region. No single particle needs to know where the lamp is. No electron must carry a message from your finger to the filament. The entire connected circuit reorganizes, and energy begins flowing through the electromagnetic pattern established around it. What reaches the lamp quickly is not a particular electron completing a heroic journey, but a change passing through a system already filled with charge. The wire carries electricity because countless electrons respond together, each moving only modestly on average, while the field linking them allows the effect to travel with remarkable speed. The current looks like a stream only from a distance. Beneath that simple appearance is a collective quantum motion in which the particles move slowly, the signal moves quickly, and the energy follows an invisible path shaped by the whole circuit. The strange reason. Some materials conduct and others insulate. Two objects can look equally solid, feel equally smooth, and contain equally ordinary atoms. Yet one will carry electric current easily, while the other will almost completely refuse. And the difference is not simply that one contains more electrons. Every material contains electrons, but conductivity depends on whether those electrons have accessible ways to change their motion when an electric field is applied. Inside a single isolated atom, electrons can occupy only certain allowed energy states. When huge numbers of atoms join together to form a solid, those individual states spread into wide ranges containing an enormous number of closely spaced possibilities. Some of these ranges are filled with electrons, while others may remain partly or completely empty. The crucial question is whether electrons near the highest occupied states can move into nearby available states without requiring a large amount of extra energy. In a conductor such as copper, the electronic structure leaves accessible states extremely close to the ones already occupied. When an electric field is applied, many electrons can shift their collective motion slightly because the material offers somewhere for them to go. They do not need to escape from the metal or leap from atom to atom like insects crossing stones. Their quantum states extend through the crystal, and the field changes how those states are occupied, creating an electrical current. An insulator presents a very different landscape. Its lower energy electronic states are filled, while the next available group lies much higher. The separation between them is called an energy gap. Under ordinary voltages and temperatures, the electrons cannot easily reach those empty conducting states, so the material strongly resists sustained current. The field may still shift charge by a tiny amount, slightly distorting the electron distributions inside the atoms and molecules, but the charges do not continue moving freely through the object. This is why rubber around a wire can experience an electrical field without carrying the same current as the metal hidden inside it. The distinction is not that copper has electricity and rubber does not. It is that their electrons face radically different sets of allowed possibilities. Semiconductors occupy the useful territory between these extremes. Their energy gap is large enough to limit current, but small enough that heat, light, added atoms, or an external field can move some electrons into conducting states. This makes their behavior adjustable. A semiconductor can act more like an insulator under one condition and more like a conductor under another, which is why it can be used to build sensors, switches, solar cells, and countless electronic components. Temperature exposes another important difference. In most metals, heating increases electrical resistance, because the atoms vibrate more strongly, disrupting the organized movement of electrons. In many semiconductors and insulators, heating can have the opposite initial effect. It gives more electrons enough energy to reach available conducting states, increasing the number of charge carriers. The material's conductivity is therefore determined by a competition between how many carriers are available and how easily they can move without being scattered. This is why no simple rule such as hotter means more conductive works for every substance. The outcome depends on the material's quantum structure. Crystal order also matters. In a clean, regular solid, electrons can sometimes move through extended states with relatively little disruption. Introduce impurities, missing atoms, displaced atoms, or structural disorder, and those disturbances can scatter or trap the carriers. Yet impurities are not always harmful. In semiconductors, carefully selected foreign atoms can create additional electrons or accessible vacancies, making conductivity easier to control. A tiny amount of added material can change electrical behavior by many orders of magnitude because it introduces new states into the energy landscape. This precision is one of the reasons the purity of electronic materials must be controlled so carefully. One unwanted atom among millions may sound insignificant, but at microscopic scales it can become a site that captures charge, changes current, or causes a device to fail. Some materials conduct through particles other than freely moving electrons. Salt water carries current because dissolved positive and negative ions travel in opposite directions through the liquid. In a battery electrolyte, ions move while electrons are forced to take an external route. Certain ceramics conduct oxygen ions or other charged atoms at high temperatures, making them useful in fuel cells and sensors. Even pure water is not a perfect insulator, though it conducts weakly because only a very small fraction of its molecules naturally separate into charged components. Tap water conducts much better because it contains dissolved salts and minerals. The statement that water conducts electricity is therefore incomplete. The current is usually carried largely by the ions dissolved within it, and the conductivity changes dramatically with purity and composition. Air offers another surprising example. Under normal conditions, it is a strong insulator because its electrons remain bound to molecules and very few free charges are available. Apply a sufficiently intense electric field, however, and electrons can be torn from molecules. These freed electrons collide with others, producing more charged particles in a rapid cascade. The air becomes plasma and suddenly conducts, creating a spark or lightning bolt. An insulator has not violated its identity. The conditions have transformed its electronic structure enough to create carriers and pathways that were previously unavailable. Almost any insulating material can break down if the field becomes strong enough. Plastic can char, glass can be damaged, and air can become luminous. Conductivity is therefore not an eternal label but a behavior under particular conditions. Pressure, temperature, chemical composition, light and electric field can all alter the answer. Carbon demonstrates this dramatically. Diamond and graphite are made from the same element, yet they conduct very differently because their atoms are connected in different arrangements. In diamond, each carbon atom forms a rigid three-dimensional network that locks electrons into strong bonds and leaves a large energy gap, making diamond an excellent electrical insulator. In graphite, carbon atoms form flat sheets, and some electrons occupy states that allow them to move along those layers, giving graphite useful conductivity. The identity of the atoms alone does not determine the result. Arrangement changes the available electronic states, and those states decide how charge can respond. This is why material science is not merely a catalogue of elements. The same atoms can create substances with entirely different electrical, optical, and mechanical properties when organized differently. There are even materials that abandon ordinary resistance almost completely. Below a critical temperature, certain substances become superconductors. Their electrons form coordinated quantum pairs that move through the material, without the usual scattering responsible for resistance. This does not mean all electrons suddenly travel infinitely fast, nor does it mean the material produces endless energy. It means an established current can persist without continually losing electrical energy as heat. Superconductivity requires special conditions and deserves its own explanation, but it reveals how deeply conductivity depends on collective quantum organization, rather than on a simple count of movable particles. When you hold an insulated cable, then, you are holding two materials placed together because their electrons answer the same electric field in opposite ways. The metal core provides abundant accessible states through which charge can respond, while the surrounding polymer keeps its electrons bound within arrangements that resist long-range motion. One guides current, the other confines it. The safety of the cable depends on that contrast remaining intact. If the insulation cracks, melts, becomes wet, or is exposed to excessive voltage, the forbidden path may become available, and current may reach somewhere it was never intended to go. The quiet division between conductor and insulator is what allows electricity to be controlled rather than merely released. And perhaps this is the strangest lesson hidden inside ordinary materials. Electrical behavior is not determined by how many charged particles matter contains, because all matter contains them. It is determined by opportunity, whether quantum rules provide nearby states, mobile carriers, and continuous routes through which charge can reorganize. A conductor says there is somewhere else for the electrons to be. An insulator says the next permitted place is too far away. The visible object tells you almost nothing about which answer lies inside, but the invisible structure of its allowed energies decides whether electricity will flow, hesitate, or stop. A camera sensor catches reality one photon at a time. A camera does not capture a complete scene all at once. It waits in darkness while countless individual photons arrive and leave tiny electrical traces behind. When you point a camera toward a face, a landscape, or a dim street at night, light reflected from that scene passes through the lens and is focused onto a sensor covered with millions of microscopic light-sensitive sites called pixels. Each pixel acts like a small collector, but it does not receive color, shapes, or meaning directly. It receives photons, one by one, and converts some of their energy into electrical charge. In most modern cameras, the sensor is made from silicon, a material whose electrons can be lifted into mobile states when they absorb photons carrying enough energy. A photon enters the sensor, interacts with the silicon, and may free an electron from a bound state, leaving behind a corresponding vacancy. The camera then traps and counts the resulting charge inside each pixel during the exposure. A bright region of the scene sends many photons, producing more charge. A dark region sends fewer, producing less. By the time the shutter closes, the sensor contains a vast map of electrical values, each one representing how much light reached a particular location. The image begins not as a picture but as millions of small numerical measurements. Yet even this description is slightly too neat, because photons arrive randomly. Aim a camera at a surface under perfectly steady illumination and repeat the photograph many times, and the number of photons collected by each pixel will not be exactly identical in every exposure. Light arrives according to quantum probability, so some pixels receive slightly more photons and others slightly fewer. This natural fluctuation is called photon shot noise, and it becomes especially noticeable in darkness. In bright daylight, a pixel may collect so many photons that the random difference is a tiny fraction of the total and the image appears smooth. At night, when only a small number arrive, the variation becomes significant. One pixel may receive 12 photons, while a neighboring pixel receives 8, even though both were looking at nearly the same brightness. After amplification, those small differences appear as grain or speckling. Some of the noise in a dark photograph is therefore not caused by a cheap camera or faulty software. It comes from the quantum statistics of light itself. The camera cannot record photons that never arrived, and no algorithm can perfectly reconstruct information that was never physically collected. A longer exposure helps because it gives the sensor more time to gather light, improving the balance between the real signal and random fluctuation. A wider lens opening also allows more photons through, but both choices have consequences. Longer exposures can blur movement, while wider apertures reduce the range of distances that appear sharply focused. Photography is therefore partly the art of deciding how to spend a limited supply of photons. Each pixel also has a maximum capacity. It can collect only a finite amount of charge before it becomes saturated. Once full, additional photons cannot make it record a brighter value, so details in intense highlights disappear into pure white. At the opposite extreme, very weak signals may be buried beneath electrical noise produced by the sensor and its electronics. The range between the faintest usable signal and the brightest unsaturated one is the camera's dynamic range. A scene containing a dark interior and a sunlit window may exceed that range, forcing the camera to sacrifice detail in the shadows, the highlights, or both. Human vision handles such scenes differently, because your eyes and brain continually adapt, shift attention, and combine information over time. A camera must turn one exposure into a fixed record, so it often relies on multiple exposures and computational processing to imitate what seems effortless to you. Color adds another layer of construction. Most camera pixels measure only the total number of photons they absorb and do not independently identify each photon's color. To estimate color, manufacturers place a mosaic of tiny filters over the sensor, commonly using red, green, and blue filters. Each filtered pixel records only part of the incoming spectrum. Because human vision is especially sensitive to detail in the green region, many common filter patterns include more green-sensitive pixels than red or blue ones. The camera's processor then examines neighboring measurements and estimates the missing color information for every location through a process called demosaicising. The final photograph therefore contains full-color pixels that were not measured directly in that exact form. They were reconstructed from nearby photon counts, filtered through assumptions about how natural scenes usually vary. Fine repeating patterns can confuse this reconstruction and create false colors or rippling effects known as moire. Once again, the image you see is not a simple copy of the light that arrived. It is an informed interpretation built from incomplete samples. Before the photons even reach the sensor, the lens has already shaped which ones are allowed to contribute. The lens bends incoming light so that photons from one point in the scene are concentrated near a corresponding point on the sensor. If the focus is wrong, those photons spread over a wider area and the detail becomes blurred. A lens aperture limits the angles from which light can enter, influencing brightness, sharpness, and depth of field. Even a perfectly manufactured lens faces diffraction, a wave effect that causes light passing through a small opening to spread. Closing the aperture can improve some optical flaws, but close it too far, and diffraction softens the image. There is no setting that simply produces unlimited sharpness, because the camera must negotiate the physical behavior of light. The sensor itself is not perfectly efficient either. Some photons are reflected, some pass too deeply, some are absorbed in regions where their charge cannot be collected, and others lack the right energy to produce a useful response. Quantum efficiency describes the fraction of arriving photons successfully converted into measurable electrons. Modern sensors can perform remarkably well, but they never catch everything. Microscopic structures such as tiny lenses placed above each pixel help guide more light into the sensitive region, especially as pixels become smaller. Smaller pixels allow more spatial detail on a compact sensor, but each one has less area in which to collect photons, making low light performance more difficult. Larger sensors often perform better in darkness, partly because they can gather more total light for the same framing and exposure conditions. This is not because large cameras possess better-looking photons. They simply collect a larger sample from the scene. Increasing the camera's ISO setting does not make the sensor physically catch more light. It amplifies the electrical signal already collected, along with much of the noise. The photograph becomes brighter, but the missing photons do not reappear. Modern processing can reduce visible noise by comparing neighboring pixels, combining multiple frames, and using learned patterns to estimate likely details. Yet these methods involve trade-offs. Too much smoothing can erase fine texture, while aggressive sharpening can invent edges that were never clearly recorded. Computational photography in phones goes further by capturing several exposures before and after you press the button, aligning them, selecting sharp regions, brightening shadows, protecting highlights, reducing motion blur, and combining the results into one image. The final photograph may represent no single instant exactly. It is a synthesis built from several brief photon collections. This can produce a clearer and more useful image than one raw exposure, but it also raises a quiet question. At what point does recording become interpretation? Every camera has always interpreted to some degree through lens choice, film chemistry, sensor response, color processing, and exposure. Digital methods simply make that transformation more visible. Even a raw image file is not untouched reality. It contains measurements shaped by filters, electronic gain, sensor temperature, defective pixel correction, and the limits of the device. Cameras used in astronomy reveal the photon-by-photon nature of imaging most dramatically. When scientists photograph extremely faint galaxies, they may expose a sensor for long periods and combine many observations. Individual photons can be so scarce that distinguishing a real celestial object from random noise requires careful statistics. Sensors are often cooled to reduce unwanted electrical activity generated by heat. Cosmic rays can strike the detector and leave bright marks unrelated to the target. Researchers identify and remove these events while preserving genuine signals. An astronomical image may look like a smooth, colorful window into space, but it can begin as a sparse collection of photon impacts accumulated across hours and processed with extraordinary care. The camera never receives the galaxy as a complete object. It receives delayed fragments of its light, some of which may have traveled for millions or billions of years before releasing a single electron inside the detector. The same principle applies when you take an ordinary portrait. No pixel contains a miniature face. Each holds a charge influenced by how many photons reached it, and the processor assembles those measurements into boundaries, tones, and colors. Your own brain then completes the final step, recognizing an expression, remembering a person, and attaching emotion to the pattern. Lasers are quantum order turned into light. A laser beam looks like ordinary light made unusually bright, but its real strangeness lies in how precisely its photons are organized. The word laser comes from light amplification by stimulated emission of radiation, and every part of that name describes a quantum process. In most familiar light sources, atoms and molecules release photons independently. A hot filament, a flame, or the sun produces light from an enormous number of unrelated events. So the emitted waves begin at different times, travel in many directions, and carry a broad mixture of wavelengths. Laser light is different because its photons are produced through a chain reaction that encourages them to match. They tend to share the same frequency, move in nearly the same direction, and remain closely related in phase, meaning the rises and falls of their wave-like behavior line up with unusual consistency. This organized state is called coherence, and it allows laser light to remain narrow, travel great distances with limited spreading, and be focused into an extremely small region. The process begins inside a gain medium, which may be a gas, a crystal, a liquid, a semiconductor, or even a carefully designed optical fiber. The atoms or electrons in this material can occupy only certain quantum energy states. An external energy source known as the pump raises many of them into excited states. The pump might be an electric current, another light source, or a chemical reaction, depending on the laser. Excited states do not last forever. Left alone, an atom may eventually drop to a lower energy and release a photon spontaneously, but spontaneous photons leave at unpredictable moments and in random directions. A laser becomes possible through a second process called stimulated emission. If a photon with the right energy passes near an excited atom, it can encourage that atom to release its stored energy as another photon. The remarkable part is that the new photon matches the stimulating one in crucial ways. It has the same frequency, travels in the same direction, and joins it with the same phase relationship. One photon becomes two coordinated photons, which can stimulate more excited atoms and create still more matching photons. This is not copying in the ordinary sense, and the photons are not stamped like identical coins by a machine. The matching behavior follows from the quantum rules governing the interaction between light and the excited material. For this chain reaction to grow, the laser must achieve population inversion, a condition in which more particles occupy an excited state than the lower state into which they can release light. Under normal thermal conditions, lower energy states are more heavily populated, so incoming photons are more likely to be absorbed than multiplied. The pump drives the material away from that ordinary balance and creates a temporary reservoir of excited particles. Once enough of them are available, stimulated emission can dominate, allowing light to be amplified rather than swallowed. The gain medium is usually placed between two mirrors, forming an optical cavity. Photons traveling along the correct path bounce back and forth through the material, stimulating repeated emissions and building a stronger field. One mirror reflects nearly all the light, while the other allows a small fraction to escape. That escaping fraction becomes the laser beam. The mirrors do more than trap light. The distance between them permits only particular standing wave patterns to survive efficiently, selecting certain frequencies and suppressing many others. The cavity therefore acts as a filter and an organizer, repeatedly rewarding light that fits its geometry. The final beam is not perfectly uniform or infinitely narrow, but compared with ordinary light, it can be extraordinarily ordered. This is why a small laser pointer can place a visible spot on a distant wall, while the light from a household bulb spreads throughout the room. Brightness alone is not the key. A powerful lamp may release far more total light, yet most of it travels in unrelated directions. The laser concentrates a smaller or larger amount of energy into a carefully controlled stream. Its photons cooperate statistically, producing a beam that can be directed, measured, and manipulated with great precision. The single color associated with many lasers also comes from the selected energy transition and the optical cavity. Although real lasers are not always perfectly monochromatic, every beam has some range of frequencies, and certain lasers are intentionally designed to produce several wavelengths or extremely short pulses containing a broader spectrum. A laser used in a barcode scanner, a fiber optic network, a surgical instrument, and an industrial cutting machine may rely on the same basic principle while differing enormously in power, wavelength, pulse duration, and construction. In a supermarket scanner, the beam reflects differently from dark bars and pale spaces, allowing a sensor to decode a pattern. In optical communication, a laser is switched or modulated rapidly so information can travel through transparent fibers as controlled changes in light. Because the beam is coherent and well-directed, it can carry signals across great distances with low loss, though repeaters and amplifiers are still needed in long networks. In medicine, carefully chosen wavelengths can cut tissue, reshape the cornea, seal blood vessels, or target pigments. The result depends not merely on the presence of laser light, but on how strongly a particular tissue absorbs that wavelength, how long the pulse lasts, and how concentrated the energy becomes. A beam that is safe when spread across a broad area can become destructive when focused to a tiny point. This is why even low-powered lasers can damage the retina. The eye's lens can concentrate an incoming beam onto a very small region, sharply increasing the energy delivered to delicate tissue. The beam may look harmless because it contains no flame and produces little sensation before injury occurs, but its order allows it to be focused far more effectively than ordinary diffuse light. Industrial lasers use the same advantage on a larger scale. A concentrated beam can melt, vaporize, weld, engrave, or measure materials without physical contact. Pulsed lasers can release energy in bursts, so brief that they remove tiny regions before heat spreads far into the surroundings. Scientists use even shorter pulses to study chemical reactions unfolding in extraordinarily small fractions of a second. Other lasers measure distance by sending out light and timing its return, revealing the shape of landscapes, buildings, clouds, and even the surface of the moon. Holography also depends on coherence. When laser light from an object overlaps with a reference beam, the two form an interference pattern that records not only brightness, but information related to the light's phase. When illuminated correctly, that pattern can reconstruct a three-dimensional looking wavefront. Ordinary lamps usually lack enough coherence for this delicate structure to remain stable. Yet laser order has limits. Photons in a beam are not tiny soldiers moving in a perfect line, and a laser does not eliminate quantum uncertainty. The beam still diffracts and spreads, mirrors absorb some energy, the gain medium heats, and spontaneous emission introduces noise. At very low light levels, the number of photons fluctuates. Engineers must manage these imperfections through cooling, precise mirrors, stable power supplies, and careful control of the cavity. The extraordinary result is not perfection but sustained organization despite unavoidable disturbance. This is what makes a laser more than a bright ray. It is a machine that prepares matter in an unusual energetic condition, uses one photon to trigger the release of another, repeatedly selects the light that fits its internal structure, and allows a small portion of that ordered field to leave. Nothing inside it commands the photons individually. No central controller tells each one where to travel. Order emerges because the quantum process favors matching emission, and because the cavity preserves certain patterns while others fade. A laser is therefore a vivid example of how large-scale precision can arise from microscopic rules. You see a clean red line crossing a room, but hidden behind it are excited states, stimulated transitions, resonant modes, and countless interactions reinforcing the same pattern. Ordinary light is often a crowd of unrelated voices. Laser light is closer to a choir holding one note together, not because nature has become simpler, but because the device has arranged quantum events so that they amplify one another. What leaves the laser is not merely energy made brighter. It is quantum order made visible. The quantum reason gold looks golden. Gold does not look golden simply because it is gold. Its color appears because the electrons inside its atoms move under conditions so extreme that Einstein's relativity quietly changes the way the metal interacts with light. Most metals look silvery because their mobile electrons reflect a broad range of visible wavelengths with roughly similar efficiency. Silver, aluminum, and many polished metals therefore return much of the visible spectrum to your eyes without strongly favoring one region, producing the familiar bright grey-white shine. Gold breaks that pattern. Its atoms contain 79 protons, creating a very strong electrical attraction near the nucleus. The innermost electrons move through this intense environment at speeds that are a significant fraction of the speed of light. Under these conditions, ordinary non-relativistic quantum mechanics is no longer enough. Relativistic effects alter the energies and shapes of certain electron states, especially those involved in gold's interaction with visible light. One important state is pulled closer to the nucleus and stabilized, while another is shifted in a different way. The energy separation between them becomes smaller than it would be in a lighter atom with similar chemical structure. This change has a visible consequence. Gold can absorb blue and violet light more strongly than many other metals. Because some of the shorter visible wavelengths are removed from the reflected light, the mixture that returns to your eyes is richer in red, orange, and yellow. Your visual system interprets that imbalance as the warm golden color that has made the metal recognizable across cultures and history. Without relativistic effects, theoretical calculations suggest that gold would look much more like silver. Its famous color is therefore not merely a surface decoration or an accidental pigment. It is a large-scale consequence of electrons moving in the powerful field of a heavy atomic nucleus. The color also shows why the periodic table cannot always be understood through simple repetition. Gold lies beneath silver and copper in the same chemical family, and all three share important electronic features. Yet their appearances differ. Copper also absorbs part of the higher energy visible spectrum, leaving it reddish, while silver reflects visible light more evenly and appears white. In gold, the nucleus is heavy enough for relativistic changes to become especially important. pushing its optical behavior farther away from the pattern you might expect. This is one reason heavy elements sometimes possess surprisingly unusual properties. The electrons closest to a highly charged nucleus do not experience the same conditions as those in lighter atoms, and when their energies shift, the chemistry and appearance of the whole element can change. Gold's color is not the only result. Relativistic effects also contribute to the strength of its chemical bonds and help explain why gold remains solid at ordinary temperatures, while mercury, the next element in the periodic table, is liquid. In mercury, relativistic stabilization affects the outer electrons in a way that weakens bonding between neighboring atoms, making the metal unusually reluctant to form a rigid structure. Gold and mercury sit beside each other, yet one forms a dense, enduring solid and the other flows. The contrast reveals how the behavior of visible matter can depend on subtle shifts in invisible electron states. Gold's surface adds another layer to its appearance. Like other metals, it contains electrons that can respond collectively to incoming light, creating strong reflection and the characteristic metallic luster. But the reflected spectrum is shaped by those allowed electronic transitions. Pure gold appears richly yellow, while the exact shade changes when it is mixed with other metals. Jewelers rarely use completely pure gold for everyday objects, because it is soft and can be scratched or bent easily. Adding silver, copper, palladium, nickel, or other metals changes both its strength and its optical response. Copper-rich alloys create rose or red gold. Silver and certain pale metals can lighten the color. White gold is not naturally identical to platinum. It is an alloy designed to reduce gold's yellow appearance and is often coated with rhodium to create a brighter white surface. The color of a ring therefore contains information about its microscopic composition. Two pieces may both be called gold, while reflecting light differently, because their atoms are mixed in different proportions and arranged into slightly different electronic structures. Gold can even stop looking golden when divided into extremely small particles. In bulk metal, light interacts with an extended sea of electrons across the surface. In nanoparticles, those electrons can oscillate collectively at frequencies determined by the particle's size, shape, and surroundings. These oscillations, known as localized surface plasmons, can cause tiny gold particles to absorb and scatter colors very differently from a solid bar. A suspension of small gold nanoparticles may appear ruby red, purple, or even blue rather than yellow. Medieval artisans produced red-stained glass using gold particles long before they understood the quantum and electromagnetic reasons. The same element that shines warmly in a coin can create deep crimson in glass because changing scale changes how its electrons respond to light. This property is now used in sensors, medical research, imaging methods, and experimental treatments, where gold nanoparticles can be designed to interact with selected wavelengths. Their color can shift when molecules attach to their surfaces or when particles move closer together, allowing researchers to detect microscopic chemical changes through visible signals. Gold's appearance is therefore not one permanent color embedded inside each atom. A single isolated gold atom is not a tiny yellow speck. The familiar metallic color emerges only when enormous numbers of gold atoms form a solid and their electron states combine into the structure of a metal, alter the particle size, surface, alloy composition, or surrounding material, and the optical behavior changes. This is another reminder that many properties belong to organized collections rather than to individual particles. The nucleus supplies the conditions. Quantum mechanics supplies the allowed states. Relativity shifts those states. And the solid structure turns those shifts into a color large enough for your eyes to see. Gold's resistance to corrosion helps preserve that color. Many metals react readily with oxygen, water, or chemicals in the environment, building dull surface layers that change how light is reflected. Iron rusts, copper develops dark oxides and eventually a green patina. Silver tarnishes when sulfur compounds form a dark layer. Gold is unusually unreactive under ordinary conditions, so its metallic surface can remain exposed for long periods without being hidden beneath corrosion. This chemical stability does not create the golden hue, but it allows the hue to survive. Ancient gold objects can retain their shine for thousands of years because the atoms at the surface are reluctant to abandon their metallic state. That endurance helped gold become associated with permanence, royalty, divinity, and wealth. But the cultural meaning rests upon a physical foundation. Humans valued the color because it was rare and striking, and they trusted the material because it resisted decay. What appeared symbolic was supported by electron behavior. There is something quietly remarkable in this. When you look at a gold coin or a polished ring, you are seeing relativity without needing a telescope, particle accelerator, or journey near a black hole. The same theory, often associated with warped space-time and cosmic speed limits, is present in the warm reflection of an object held between your fingers. Electrons moving within a heavy atom experience relativistic changes. Those changes reshape quantum energy levels. Those levels decide which wavelengths are absorbed, and the surviving light becomes gold in your perception. The color seems ancient, simple, and almost emotional, yet it is built from some of the deepest rules known to physics. Gold looks golden because matter at the smallest scale does not obey the comfortable boundaries between quantum theory and relativity. Inside every shining surface, the two are already working together, turning the invisible motion of electrons into one of the most recognizable colors in the human world. Water molecules are never truly still. A glass of water may look perfectly calm, but on the molecular scale, it is a crowded world in constant motion, rearranging itself so quickly that stillness exists only in the picture seen by your eyes. Each water molecule is made from one oxygen atom joined to two hydrogen atoms, creating a bent shape with an uneven distribution of electrical charge. The oxygen side carries a slight negative character, while the hydrogen side carries a slight positive one, and this polarity allows neighboring molecules to attract each other through hydrogen bonds. These bonds are not rigid bars locking the liquid into place. They form, bend, weaken, and break continually, often surviving for only tiny fractions of a second before new ones replace them. A cup of water is therefore not a collection of independent molecules drifting without structure, nor is it a fixed network like a crystal. It is a temporary, shifting web in which each molecule is constantly changing partners. At room temperature, the molecules move rapidly, rotating, vibrating, and traveling through the liquid while colliding with those around them. Some move faster, others more slowly, because temperature does not give every molecule the same speed. It describes the overall distribution of their kinetic energy. Even when the water appears motionless, this microscopic movement continues in every direction, and the random motions cancel at the larger scale, leaving no visible current. The calm surface is not the absence of movement. It is the balance of countless movements too small and disordered to create one shared direction. This hidden motion explains diffusion. Place a drop of dye into still water, and even without stirring, its molecules gradually spread. Water molecules collide with the dye from all sides, sending it along an irregular path until the color becomes more evenly distributed. The process can be slow in a glass, but it reveals that matter does not need a visible flow to transport particles. Random molecular motion is enough. The same principle helps dissolved oxygen reach aquatic organisms, allows salts to spread through body fluids, and carries molecules through cells. Life depends on fluids that never become microscopically quiet. Temperature changes the speed of this motion. Heat water and its molecules move more energetically, breaking and rebuilding their hydrogen bond network more rapidly. Some molecules near the surface gain enough energy to escape into the air as vapor, even when the water is far below its boiling point. This is evaporation. The fastest molecules are more likely to leave, so the molecules remaining behind have a lower average energy, which cools the liquid. That is why sweat can cool your skin. The water molecules that escape carry energy away. Boiling is different. It begins when vapor bubbles can form throughout the liquid, because the vapor pressure becomes strong enough to compete with the surrounding pressure. The water does not suddenly begin moving at the boiling point. It was already moving. Boiling marks a change in how that motion reorganizes the liquid into gas. Cooling water reduces its average molecular energy, but it does not make the molecules instantly motionless. As liquid water approaches freezing, the hydrogen bonds begin arranging molecules into the open, ordered structure of ice. This structure contains more space than the constantly shifting arrangement in liquid water, which is why ice is less dense and floats. That familiar fact is unusual. Most substances become denser when they freeze, but water's bent molecular shape and hydrogen bonding create a crystal pattern that expands. If ice sank, lakes in cold climates could freeze from the bottom upward, changing aquatic environments dramatically. Instead, floating ice forms an insulating layer above the water beneath it. The restless molecular character of water and the unusual order of its frozen state have helped shape life on Earth. Yet even ice is not perfectly still. Its molecules remain fixed near positions in a crystal lattice, but they continue to vibrate. As the temperature falls, those vibrations weaken, but quantum mechanics places a limit on how completely motion can disappear. In the lowest possible energy state, a molecular system still retains what is called zero-point motion. This does not mean the ice contains ordinary heat at absolute zero, nor that its molecules wander freely through the solid. It means that quantum particles cannot possess perfectly fixed positions and absolutely zero motion at the same time. Complete microscopic stillness is not an allowed state of nature in the simple classical sense. Water also behaves strangely under pressure and confinement. Inside narrow biological channels, mineral pores, or microscopic gaps, its hydrogen bond network can differ from that of an open glass. Molecules near a surface may align or move differently because they interact with nearby atoms. In cells, water is not merely a passive background in which biological molecules float. It surrounds proteins, ions, membranes, and genetic material, influencing their shape and activity. Proteins fold partly because some regions interact favorably with water while others avoid it. Ions become surrounded by shells of oriented water molecules, changing how they travel and react. Much of life's chemistry depends not only on substances dissolved in water, but on the motion and organization of the water itself. Even the sensation of wetness does not come from a special wetness receptor in your skin. Your brain combines temperature, pressure, friction, and movement to infer that water is present. The liquid cools the skin, changes how surfaces slide, and moves into microscopic textures, creating a pattern your nervous system learns to interpret. Once again, the still-looking substance proves to be active in ways your senses summarize rather than reveal directly. A cup left on a table may appear unchanged for hours, but molecules are evaporating from its surface. Others are returning from the air, dissolved gases are moving, temperature is being exchanged with the room, and the hydrogen bond network is rebuilding itself again and again. If the water is exceptionally pure and undisturbed, it can even remain liquid slightly below its normal freezing point until a vibration or impurity triggers ice formation. The apparent calm can hide a state ready to reorganize suddenly. Water's stability is therefore not the same as inactivity. It is a dynamic balance maintained by continuous motion, and perhaps that is the quiet truth contained in every glass you lift. The liquid seems peaceful because its countless molecular journeys have no single visible destination. Beneath the surface, bonds are forming and vanishing, molecules are spinning and colliding, and energy is passing through a network that never repeats itself exactly. Water is never truly still, yet from that restless movement emerges something stable enough to fill oceans, circulate through living bodies, shape climates, and carry life. What appears motionless is not frozen in time. It is motion so evenly shared that, from where you sit, it looks like peace. The strange quantum life of a cup of coffee. A cup of coffee looks like a simple brown liquid, yet before it reaches your lips, it has already passed through a chain of quantum events that began inside a living plant and continued through roasting, grinding, brewing, cooling, and finally perception. The strangeness does not come from the coffee behaving like a laboratory particle experiment or existing in several cups at once. It comes from the quieter fact that every flavor, aroma, color, and chemical reaction inside it depends on electrons occupying specific states and molecules being allowed to change only in particular ways. The story begins in the seed. A coffee bean is not really a bean, but the seed of a fruit, built by a plant that used sunlight to assemble carbon dioxide, water, minerals, and nitrogen-containing compounds into sugars, acids, proteins, oils, caffeine, and structural material. Those substances remain relatively mild while the seed is green, but roasting drives them into a radically different chemical world. As the bean heats, water escapes, cell walls weaken, sugars begin to break apart, and amino acids react with sugars through a vast collection of processes known as the Maillard reaction. There is no single coffee molecule responsible for the result. Roasting produces hundreds of volatile compounds and many larger, darker molecules, some contributing caramel-like sweetness, others nutty, fruity, smoky, spicy, earthy, or bitter notes. Every reaction is governed by quantum chemistry, because chemical bonds are arrangements of electrons, and a reaction can proceed only when molecules collide in a suitable orientation and enough energy is available to reorganize those bonds. Heat does not tell molecules what flavor to become. It increases their motion and gives more of them opportunities to cross reaction barriers, after which their electronic structures determine which new combinations are possible. This is why a small change in roasting temperature or duration can produce a noticeably different cup. A lighter roast preserves more of the bean's original acids and delicate aromatic compounds, while a darker roast drives further decomposition, producing heavier roasted flavors and often greater bitterness. The change is not merely that the bean becomes hotter or darker, its molecular identity is being rewritten. Grinding begins another transition. A whole roasted bean protects much of its chemistry within a relatively small exposed surface, but breaking it into thousands of particles suddenly opens new paths for oxygen and water. Aromatic molecules escape more quickly, oils become exposed, and oxidation begins altering flavor. This is why freshly ground coffee can smell intensely vivid and then seem flatter not long afterward. The aroma has not vanished mysteriously. Many volatile molecules have diffused into the air, while others have reacted into forms your nose detects less easily. When hot water reaches the grounds, brewing becomes a selective extraction rather than a simple act of dissolving coffee into water. Different molecules leave the particles at different rates according to their size, polarity, location, solubility, and interaction with the surrounding material. Acids and some aromatic compounds can emerge relatively early. Sugars, bitter compounds, oils, caffeine, and larger molecules follow according to the brewing method and conditions. Water temperature, grind size, contact time, agitation, and pressure all change which substances are extracted and in what proportions. Grind too coarsely or brew too briefly, and the cup may taste thin or sharply sour because extraction remains incomplete. Grind too finely or leave the water in contact too long, and additional bitter or drying compounds may dominate. This does not mean sourness always proves under extraction, or bitterness always proves over extraction, because the bean, roast, water, and method all matter, but the general pattern reveals that brewing is controlled molecular separation. You are using water to choose which parts of the roasted seed will enter the drink and which will remain behind. Espresso adds pressure, forcing hot water through a compact bed of finely ground coffee in a short time. The creamy layer on top, called creamer, contains tiny gas bubbles surrounded by oils and other compounds. Much of the gas is carbon dioxide released from the roasted beans, where it had remained trapped in microscopic spaces after roasting. Fresher beans often produce more creamer because they still contain more gas, though abundant creamer does not automatically mean better flavor. Filter coffee follows a slower route, and the paper filter can hold back some oils and fine particles, producing a cleaner texture than methods that allow more suspended material into the cup. The brewing device therefore changes not only concentration but the physical composition of what reaches your tongue. Caffeine is one of the most famous molecules in coffee. but it contributes less to the aroma than many people assume. It is largely odorless and strongly bitter, and its most noticeable effect begins after absorption. In your brain, caffeine resembles a molecule called adenosine, closely enough to occupy certain adenosine receptors without activating them in the usual way. Adenosine gradually accumulates during waking hours and helps promote sleepiness and reduced neural activity. By blocking some of its signals, caffeine temporarily reduces the feeling of fatigue. It does not create new energy inside your body. It changes how strongly you perceive one of the systems that normally tells you to slow down. This is why caffeine can make you feel more alert while leaving the underlying need for sleep unresolved. Its effects vary because people metabolize it at different rates, influenced by genetics, liver enzymes, medications, pregnancy, smoking, habitual use, and time of day. The same cup may fade quickly for one person and disturb another person's sleep many hours later. The drink is chemically similar, but the biological system receiving it is not. Before caffeine reaches the brain, however, coffee has already become an experience through smell. As you lift the cup, volatile molecules rise with the warm air and enter the nose. Some travel through the nostrils, while others reach the nasal cavity from the back of the mouth after you sip, a route known as retronasal olfaction. These molecules bind temporarily to receptor proteins, changing their shapes and triggering electrical signals. Your brain compares patterns across many receptor types and constructs the perception of chocolate, citrus, smoke, flowers, nuts, or spice. Those qualities are not labels carried by individual molecules. A single aroma compound can smell different at different concentrations, and mixtures can create impressions that none of their components produces alone. Memory and expectation also influence the result. A cup served in a familiar cafe, a quiet kitchen, or an unfamiliar place may be judged differently, even when its chemistry is similar, because flavor is built jointly from smell, taste, temperature, texture, vision, and memory. As the coffee cools, its flavor changes again. Cooling reduces the escape rate of many volatile molecules, but it can also make certain tastes easier to notice because intense heat no longer overwhelms the tongue and nose. Sweetness, acidity, and subtle fruit-like notes may become clearer, while bitterness can remain or become more prominent depending on the brew. The cup is not becoming chemically frozen as it cools. Oxygen continues to react with compounds at the surface. Aromas continue to leave. Suspended particles settle, and oils may gather into thin films. Add milk, and proteins and fats bind, surround, or dilute some flavor molecules, softening bitterness and changing how aromas are released. Add sugar, and sweetness does more than introduce a separate taste. It can suppress the perception of bitterness through interactions in the sensory system. The final experience is therefore not a straightforward reading of the liquid's ingredients. It is a negotiated result between molecules and a living observer. Quantum physics remains beneath every step, but in a disciplined, non-magical way. It determines the shapes of molecules, the strength of their bonds, the colors produced during roasting, the wavelengths of infrared energy the hot cup emits, the reactions by which aroma compounds form, and the receptor interactions that eventually become taste and alertness. Yet by the time you hold the cup, those quantum rules have scaled upward into chemistry, thermodynamics, biology, and memory. You do not taste electrons. You taste an emergent pattern created by an enormous number of molecular events. And perhaps this is what makes an ordinary cup of coffee so quietly remarkable. It is not one substance delivering one effect, but a temporary meeting of plant biology, controlled heat, selective extraction, airborne chemistry, neural interpretation, and time. The cup begins changing before you take the first sip and continues changing while you drink it. Its aromas escape, its temperature falls, its molecules interact with your body, and its meaning becomes attached to the moment in which you experience it. Coffee does not need to violate reality to be strange. Its real mystery is that invisible quantum rules can pass through so many layers of organization and emerge as warmth in your hands, bitterness on your tongue, alertness in your mind, and a brief feeling that the day has finally begun. Every object around you is vibrating at the smallest scale. Nothing in the room is as still as it appears, because every object around you is carrying a hidden choreography of motion beneath its silent surface. The shelf on the wall, the glass in your hand, the metal inside a lamp, and even the floor beneath your feet may seem motionless, only because your senses are too slow and too large to detect what is happening inside them. In a solid, atoms are not frozen in perfectly fixed positions like stones cemented into place. They are held near preferred locations by electrical forces, but they continually move around those positions, shifting back and forth in response to the energy stored within the material. The warmer the object becomes, the more energetic this motion tends to be. Yet these atoms do not usually vibrate as isolated individuals. A movement in one region affects neighboring atoms, which influence the next ones, creating coordinated patterns that travel through the material. Physicists describe the quantum units of these collective vibrations as phonons. A phonon is not a tiny particle hidden between atoms in the same way a grain of dust hides beneath a chair. It is a quantized pattern of motion, a way of describing how vibrational energy is shared across many atoms at once. This distinction matters because the smaller scale motion inside an object is not merely random shaking. Solids support particular vibrational patterns determined by how their atoms are connected, how heavy those atoms are, and how stiffly their bonds resist displacement. A crystal, with atoms arranged in a repeating structure, can support waves of vibration that move through its lattice in organized ways. An amorphous material, such as ordinary glass, lacks the same long-range repeating order, so its vibrations propagate and scatter differently. These microscopic patterns help determine properties you experience every day, including how quickly a material carries heat, how it expands when warmed, how it transmits sound, and how easily it can be damaged. When you strike a metal spoon against a cup, the sound is not produced by the entire spoon moving as one perfectly rigid object. The impact disturbs atoms near the point of contact, and that disturbance travels through the metal as elastic waves. Different vibrational modes survive for different lengths of time, producing the spoon's recognizable ringing tone. A piece of wood responds with a duller sound because its complex fibers, pores, and internal boundaries scatter and absorb vibrational energy more rapidly. The sound of an object is therefore partly a report on its hidden architecture. You hear how easily motion can travel through it. The same internal vibrations also carry thermal energy. In many non-metallic solids, heat moves largely through these collective lattice waves. The energy does not flow as a single warm substance migrating from one side to another. Vibrational disturbances pass through the material, collide, scatter, and redistribute their energy. In a well-ordered crystal, some vibrations can travel relatively far before being disrupted. In a disordered material, boundaries, impurities, and structural irregularities interrupt them more frequently, reducing thermal conductivity. This is why two objects at the same temperature can handle heat so differently, even when they appear equally solid. Their atoms may contain similar amounts of microscopic motion, but the pathways available for that motion to spread are not the same. Heating also changes the average spacing between atoms. The bonds connecting them are not perfectly symmetrical springs. As vibration becomes more energetic, atoms tend to spend slightly more time at greater separations than at smaller ones, causing the entire object to expand. The change may be too small to notice in a household object, but over long bridges, railway tracks, pipes, and buildings, thermal expansion becomes important enough to bend structures or create cracks. Engineers include joints and gaps so materials can grow and shrink as temperatures change. A bridge that looks stationary is quietly lengthening under summer heat and contracting during cold nights because its atoms are vibrating differently. Precision instruments must account for the same effect on much smaller scales. A telescope mirror, laboratory ruler, or computer component can shift enough with temperature to alter a measurement or disrupt alignment. Stillness is not only an illusion of vision, it can be a challenge for engineering. Even mechanical strength is connected to microscopic vibration. As temperature rises, atoms explore a wider range around their average positions, and defects within the material may move more easily. Metals can soften, polymers can become flexible, and brittle substances may respond differently to stress. At extremely high temperatures, the organized solid structure can no longer survive, and the material melts. Melting does not mean vibrations simply become strong enough to shake atoms loose like stones falling from a wall. It means the thermal motion and energy have become sufficient to overcome the stability of the ordered arrangement, allowing atoms or molecules to rearrange continuously. Different materials melt at different temperatures because their bonds and structures provide different levels of resistance to that reorganization. Some solids do not have one sharp melting point because their internal structure is not crystalline. Glass, for example, gradually softens across a range as molecular movement becomes easier. The nature of vibration is therefore inseparable from the nature of the material itself. Cooling reduces thermal motion, but it does not lead to the perfectly silent microscopic world classical intuition might expect. Quantum mechanics prevents a bound atom from having both an absolutely exact position and no motion at all. Even in the lowest possible energy state, a system retains zero-point vibration. This is not leftover warmth, and it cannot be removed simply by better refrigeration. It is part of the quantum ground state. The atom remains spread within a small range, rather than resting at one mathematically precise point. In light atoms or weakly bound structures, this residual motion can have noticeable consequences. It influences the properties of crystals, the behavior of helium, and the stability of certain molecular arrangements. Matter never reaches the simple state of complete mechanical stillness that the word frozen seems to imply. At the lowest temperatures, thermal motion can become extraordinarily small, but quantum uncertainty remains. Vibrations also interact with electrons and light. In some materials, an incoming photon can transfer energy into lattice vibrations, changing its own energy in the process. Spectroscopic instruments measure these shifts to identify chemical structures, crystal defects, and molecular bonds. Scientists can learn what a material is made of by studying the frequencies at which it vibrates, much as you might identify a musical instrument by its tone. Infrared radiation can be absorbed when it matches particular molecular vibrations, causing bonds to stretch or bend in characteristic ways. This allows instruments to detect gases, analyze unknown substances, and study distant astronomical objects. A molecule does not announce its identity in words. It reveals itself through the specific motions its structure permits. Even biological molecules depend on motion. Proteins are not rigid sculptures locked into one shape. Their atoms fluctuate, side chains rotate, and different regions flex, allowing molecules to bind, release, fold, and perform chemical tasks. A completely motionless protein would not simply be stable, it would often be unable to function. The living world depends on controlled movement occurring far below the scale of muscles and limbs. Yet there is no need to turn this into a mystical claim that every object is alive or consciously pulsing. Vibration is physical motion governed by energy, structure, and quantum rules. A stone vibrates, but it does not feel itself vibrating. A book contains moving atoms, but those motions do not give it thoughts. The lesson is not that still objects possess hidden minds. It is that visible stillness can emerge from enormous internal activity when that activity remains balanced and confined. The atoms in a resting object move in many directions, but their average positions remain stable. The object keeps its shape because the motions do not organize into a large shared journey. It is much like a crowded station in which thousands of people shift, turn, and walk short distances, while the building itself remains in the same place. From far away, nothing seems to happen. Up close, motion is everywhere. And perhaps that is the quiet truth surrounding you now. The room appears calm, not because matter has stopped, but because its smallest movements are held within patterns that preserve the larger form. Every silent object is filled with vibrations carrying heat, sound, stress, and quantum uncertainty through its structure. The world looks motionless only because its deepest motion is too small to disturb the shapes you recognize, allowing endless microscopic activity to gather into the peaceful illusion of rest. Why ordinary matter does not collapse into itself. Ordinary matter survives because the particles inside it are not free to settle into the smallest space imaginable, even though attraction is constantly trying to pull them inward. At first, collapse may seem like the natural fate of every atom. The positively charged nucleus attracts the negatively charged electrons. So why do the electrons not simply fall into the center and remain there? The answer is not that they are circling fast enough to avoid capture, and it is not that some hidden surface holds them apart. Atomic stability comes from the quantum nature of confinement itself. An electron cannot be squeezed into an arbitrarily tiny region without its state acquiring a much wider range of possible momenta. In simpler terms, forcing it into less space makes its motion increasingly uncertain and raises the energy of the system. The lowest energy arrangement is therefore not an electron sitting motionless inside the nucleus, but a spread-out quantum state with a finite size. Attraction pulls inward, while the energetic cost of confinement resists that compression, and the balance produces a stable atom. This is why the ground state of hydrogen has a natural scale rather than collapsing toward a point. The electron is not held at one exact distance like a bead tied to a string. Its quantum state extends through a region, and that spread is part of what keeps the atom from destroying itself. Add more electrons, and another rule becomes essential. Electrons are identical fermions, which means no two of them can occupy the same complete quantum state within the same system. This is the Pauli exclusion principle. It does not act like a conventional pushing force between tiny objects, but its consequences create an enormous resistance to crowding. As electrons fill the available states around a nucleus, later electrons must occupy different arrangements, often at higher energies. This layered filling gives atoms their electronic structure and helps create the repeating pattern of the periodic table. Carbon behaves differently from oxygen, iron differs from neon, and chemistry becomes possible because electrons cannot all descend into one identical lowest state. Matter develops structure because nature refuses to let its identical fermions become perfect copies of one another in the same place and state. When atoms form a solid, this rule continues across the entire material. The electrons belonging to neighboring atoms must be described as one combined quantum system, and they cannot all collapse into the same lowest energy arrangement. The available states fill upward, creating what physicists sometimes call degeneracy pressure. In everyday solids, this quantum resistance works together with electromagnetic bonding and the geometry of atoms to maintain volume. Compress a block of matter and you are not merely reducing empty gaps between miniature balls. You are trying to force its electrons into a smaller collection of allowed states. The particles must then occupy states with greater momentum and energy, causing the material to resist further compression. This is one reason ordinary matter occupies space instead of gathering into an impossibly dense point. The effect is not something you notice as a separate sensation, because it is already built into every chemical bond, crystal structure, and material response around you. The shape of a molecule, the spacing between atoms in a crystal, and the resistance of matter under pressure all reflect the competition between attractive interactions and quantum restrictions. Even the nucleus does not casually collapse into itself. Protons inside it electrically repel one another, while the strong nuclear force binds protons and neutrons together only across very short distances. Quantum motion also prevents the nucleons from simply settling into one motionless pile. The nucleus finds an energy balance, although that balance is not stable for every possible combination. Some nuclei contain too many protons, too many neutrons, or too much internal energy, making them radioactive. They may release particles or radiation and transform into more stable arrangements. Stability in nature is therefore not absolute stillness. It is the existence of a configuration that cannot easily lower its energy through an allowed process. Ordinary matter lasts because its common atoms and molecules occupy arrangements that are stable enough under familiar conditions. Gravity contributes almost nothing to the internal stability of a single atom because it is extraordinarily weak compared with electrical and nuclear interactions. On the scale of a person, a rock, or a building, gravity can pull objects together, but it cannot normally overcome the quantum structure of their atoms. The Earth's gravity compresses material slightly with depth, yet the pressure at the surface and throughout most ordinary environments is nowhere near enough to erase atomic structure. The world around you, therefore, remains made of recognizable solids, liquids, and gases, rather than collapsing into dense nuclear matter. But the universe contains places where gravity becomes strong enough to challenge these defenses. In a white dwarf star, the star's nuclear fuel has been exhausted, and ordinary thermal pressure can no longer support it. Gravity compresses the matter so intensely that atoms lose their familiar individual structure, and electrons move through a dense sea surrounding atomic nuclei. The star is held up largely by electron degeneracy pressure, the resistance that arises because the electrons cannot all occupy the same quantum states. This support has a limit. If the white dwarf becomes too massive, gravity can overpower the electron-based structure, driving electrons and protons together and contributing to the formation of neutrons. The object may then collapse further into a neutron star, where matter reaches densities far beyond anything found in ordinary life. Neutrons are also fermions, so neutron degeneracy pressure and nuclear interactions can resist further collapse. Yet even this resistance has a limit. If enough mass is compressed into the star, no known material pressure can stop gravity, and a black hole may form. These extreme objects reveal that matter's stability is powerful, but not unconditional. A chair does not collapse because the gravitational attraction among its particles is insignificant compared with quantum and electromagnetic effects. A massive dying star can collapse because its gravity acts collectively across an astronomical amount of matter until the usual atomic defenses are overwhelmed. The difference is not a change in the basic rules, but a change in scale and pressure. This also corrects a common misunderstanding. Matter does not remain expanded because its particles are fundamentally hard, or because empty space inside atoms acts as a cushion. It remains extended because squeezing a quantum system changes the energies and allowed states of its particles. The resistance to collapse is dynamic and mathematical, but its consequences are entirely physical. Remove quantum mechanics from the description, and electrons would radiate energy and fall into nuclei. Chemistry would vanish, solids would lose their volume, and the world as you know it could not exist. The stability of matter is therefore not an obvious background fact. It is one of the greatest achievements of quantum organization. Every object preserves its form because attraction is never acting alone. Confinement has an energetic cost. Identical particles face restrictions on how they can share states. Nuclear forces bind only under particular conditions. Stable configurations emerge from the balance among these rules. You remain a person rather than collapsing into a point because countless particles inside you are continually confined, ordered, and prevented from occupying the same states. The room appears calm, yet its entire structure depends on an invisible refusal built into nature. Matter may be compressed, reshaped, melted, broken, and transformed. But under ordinary conditions, it cannot simply abandon all distinction and descend into one final place. Its stability is not the absence of inward forces. It is the deeper fact that the universe makes collapse increasingly expensive, preserving space, structure, and complexity long enough for atoms to become worlds. Why neon signs glow like captured lightning? A neon sign is a narrow glass tube filled with an almost invisible gas, yet the moment high voltage is applied, that quiet emptiness becomes a glowing river of color that looks like lightning held perfectly still. The light does not come from a burning filament, and the gas is not hot enough to behave like a flame. Instead, the sign works by turning ordinary atoms into a temporary electrical plasma. Inside the sealed tube, the gas pressure is kept much lower than normal atmospheric pressure, leaving the atoms widely spaced compared with those in the air around you. Metal electrodes are fixed at opposite ends, and when a sufficiently large voltage is placed across them, the electric field begins accelerating the few free electrons already present in the gas. Those first electrons may come from background radiation, natural ionization, or tiny disturbances at the electrodes. As they speed through the tube, they collide with gas atoms. Some collisions simply change the electron's direction, but others transfer enough energy to lift an atom into an excited state or tear one of its electrons away completely. The newly freed electrons are then accelerated as well, producing more collisions, more ions, and more free charge. Very quickly, the gas changes from an electrical insulator into a conducting plasma. This is the moment the sign awakens. The tube is not filled with a continuous bolt of electricity traveling from one end to the other. It contains a shifting mixture of electrons, positive ions, neutral atoms, and excited atoms responding collectively to the applied field. The visible glow appears when excited atoms return to lower energy states and release their excess energy as photons. Because each element has its own allowed electronic structure, it emits a distinctive set of wavelengths. Pure neon produces the famous intense reddish-orange light associated with classic signs. Argon glows more toward violet and blue, though commercial tubes using argon often include a tiny amount of mercury. Electrical discharge excites the mercury atoms, which produce ultraviolet radiation. That ultraviolet light then strikes phosphor coatings placed on the inside of the glass, causing them to fluoresce in selected visible colors. In this way, many signs casually called neon signs contain little or no neon at all. The name has become a general label for luminous gas discharge tubing, while the actual color may come from argon, mercury, helium, krypton, xenon, colored glass, or carefully chosen phosphors. The electric discharge itself is often much more complicated than the smooth glow suggests. Near the electrodes, charge distributions create regions with different brightness and electrical behavior. Positive ions accelerate toward the negative electrode and can strike its surface, releasing additional electrons that help sustain the discharge. Farther along the tube, the plasma may settle into a more uniform glowing column. The low gas pressure is crucial. At normal pressure, electrons collide so frequently that they cannot gain much energy between impacts. Reduce the pressure too far, however, and collisions become too rare to maintain the glow efficiently. A working sign therefore depends on a carefully chosen balance. Enough space for electrons to accelerate, but enough atoms remaining for useful collisions to occur. The tube's diameter, length, gas mixture, electrode design, and operating voltage all affect the final result. Even the bends in the glass matter because they influence how the electrical field and plasma distribute themselves. Creating a sign is therefore both an artistic and technical craft. Glass tubes are heated over flames until soft, then bent by hand into letters and shapes without collapsing their hollow interiors. After the electrodes are attached, the tube is connected to a vacuum system. Air and moisture are removed because oxygen, water vapor, and other contaminants can interfere with the discharge, damage the electrodes, and alter the color. The tube may be heated and electrically processed to drive impurities from the glass and metal surfaces before the chosen gas is introduced at the correct pressure. Once sealed, the sign becomes a controlled miniature atmosphere isolated from the world outside. A transformer or electronic power supply then provides the high voltage needed to start and sustain the discharge. High voltage is necessary because the gas initially resists current. Once ionization begins, however, the plasma can conduct more easily, so the power system must limit the current. Without proper control, the discharge could increase rapidly, overheat the electrodes, damage the tube, or create an electrical hazard. This is why gas discharge lamps require ballasts, transformers, or electronic circuits, rather than being connected to a power source without regulation. The sign's soft appearance hides conditions that demand careful insulation and skilled installation. The word lightning is more than a visual comparison. A lightning bolt also begins when an electric field accelerates free electrons through a gas. Collisions create more charged particles, forming conducting channels through the atmosphere. Yet the scale and violence are entirely different. Lightning moves through air at high pressure, releases enormous energy, heats gas to extreme temperatures, and expands it explosively to create thunder. A neon tube confines a much gentler discharge within low-pressure gas and solid glass. It is not a lightning bolt shrunk down in a literal sense, but both phenomena belong to the same family of ionized gas behavior. The tube captures not the power of a storm, but its underlying principle, an electric field turning gas into a luminous conductor. This also explains why neon signs do not glow forever. The gas itself is not ordinarily consumed like fuel, but the system slowly changes. Electrode material can be eroded by ion impacts. Impurities can be released from internal surfaces. Phosphor coatings can degrade. Seals may leak, and the gas composition can become less effective. A tube may begin flickering, dimming, or glowing unevenly as pressure changes or electrodes wear. Cold weather can also alter performance, especially in mercury-containing tubes, because the mercury vapor pressure falls and the ultraviolet output weakens until the tube warms. The light that appears effortless depends on a delicate internal environment remaining within the right range. Different gas discharge technologies use related principles. Fluorescent lamps rely on mercury-generated ultraviolet light exciting a phosphor coating. Sodium vapor streetlights use excited sodium atoms to create a strong yellow-orange output. Xenon flash lamps release intense bursts useful in photography and scientific equipment. Plasma displays, once common in large televisions, use tiny gas cells that produced ultraviolet light to excite red, green, and blue phosphors. Even some modern lighting technologies that look completely different descend from the same basic idea. Electricity can prepare atoms or materials in excited states, and their return toward lower energy can become visible light. What makes the neon sign special is the way this physics is drawn directly into space. The glass tube does not merely contain light, it gives the plasma a path. Every curve guides the discharge, turning electrical excitation into handwriting, symbols, and outlines. From a distance, the tube itself disappears, and only the luminous shape remains, as though a word had been written directly into the dark. Yet no color is painted into the emptiness. The glow is renewed moment by moment as electrons accelerate. Atoms are struck, energy is stored briefly, and photons are released. Switch off the voltage, and the ordered chain stops almost immediately. The gas returns to being nearly invisible, and the bright line vanishes without leaving light behind. A neon sign therefore shines not because it contains a permanent luminous substance, but because its atoms are continually being pushed out of equilibrium and allowed to fall back again. Its beauty comes from a controlled instability, a gas kept just unsettled enough to glow, but not enough to burn, explode, or escape. What looks like captured lightning is really a carefully restrained storm at the atomic scale, repeating its brief flashes so rapidly and evenly that your eyes see one continuous ribbon of light. Why Your Microwave is a story about invisible waves. The microwave on your kitchen counter is not a small oven filled with hidden fire. It is a metal chamber that uses invisible electromagnetic waves to make certain molecules inside food respond, collide, and turn organized electrical energy into heat. When you press start, electricity powers a device called a magnetron, a vacuum tube designed to generate microwaves at a frequency commonly near 2.45 gigahertz. Inside the magnetron, electrons move under the combined influence of electric and magnetic fields, passing near resonant metal cavities that encourage electrical oscillations at a controlled frequency. Those oscillations produce electromagnetic energy, which is guided through a short passage into the cooking chamber. Microwaves are the same broad kind of phenomenon as visible light, radio waves, and infrared radiation, but they have longer wavelengths than visible light and much lower energy per photon. This matters because kitchen microwaves are non-ionizing radiation. Their individual photons do not carry enough energy to break strong chemical bonds or damage DNA by direct ionization in the way X-rays and gamma rays can. Their main effect in food is heating, and even that process is more subtle than the common claim that microwaves simply excite water molecules. Water is important because each molecule has an uneven distribution of charge, giving it a positive side and a negative side. The rapidly alternating electric field inside the oven tries to rotate these polar molecules back and forth. They cannot follow the field perfectly because they are crowded among other molecules, ions, fats, proteins, sugars, and complex structures. Their delayed, frustrated motion causes energy to be redistributed through molecular collisions and internal friction-like processes, becoming disordered thermal motion. In other words, the field creates organized molecular response, and the material converts part of that response into heat. Water is not the only substance involved. Dissolved salts can respond through ionic motion, and other polar molecules can also absorb microwave energy. Fats and sugars generally interact differently and often less strongly than liquid water at the oven's operating frequency, which is one reason different parts of a meal can heat at different rates. Frozen water behaves differently from liquid water because molecules in ice are more constrained by the crystal structure, so frozen regions may absorb microwave energy less effectively at first. Once a small area melts, the liquid water there can absorb more energy, causing that spot to heat faster and creating uneven thawing. This is why defrost settings often reduce the average power by switching the magnetron on and off, allowing heat time to spread from warmer regions into colder ones, instead of driving a few melted areas toward cooking while the rest remains frozen. The waves entering the oven reflect from its metal walls because the mobile charges in the metal rearrange in response to the electromagnetic field. These reflections create complicated standing wave patterns, with regions where the electric field is stronger and others where it is weaker. If food remained motionless in a simple cavity, some parts could sit near strong field regions and overheat, while others stayed near quieter regions and remained cool. The rotating glass plate helps move the food through different parts of the field pattern, averaging the energy over time. Some ovens also use a mode stirrer, a metal fan-like structure that alters the wave distribution without blowing hot air. The familiar hot and cold spots in reheated food are therefore not random failures. They reveal the hidden geometry of waves inside the chamber. A slice of pizza or bowl of soup can act almost like a detector, recording where electromagnetic energy was absorbed most strongly. The microwave also does not normally cook food from the inside out. Microwaves penetrate a limited distance into food, often a few centimeters depending on composition, density, temperature, and frequency. Energy is absorbed throughout that penetration region rather than only at the outer surface, which can make microwave heating seem more internal than heating in a conventional oven. But in thick foods, the center is still warmed partly by ordinary thermal conduction from surrounding regions. This is why a large dense meal may be hot near the edges and cool in the middle, and why resting time after heating is useful. During that pause, molecular motion carries energy from warmer zones toward cooler ones, reducing temperature differences even after the microwave field is gone. Stirring serves the same purpose more directly by physically mixing regions that absorb different amounts of energy. The oven's metal enclosure is essential for both efficiency and safety. It acts as a Faraday cage, confining most of the microwave energy so it reflects within the chamber instead of spreading into the room. The door contains a conductive mesh whose holes are much smaller than the microwave wavelength. Visible light, with its far shorter wavelength, passes through those openings so you can watch the food, while the much longer microwaves are strongly blocked. The door seals, interlocks, and surrounding metal geometry are designed so the magnetron cannot operate normally when the door is open. This is not because microwaves remain in the food afterward. Once the field is switched off, the radiation in the chamber disappears extremely quickly. The food does not become radioactive because heating with microwaves does not create unstable atomic nuclei. What remains is thermal energy already transferred into the material. The risk from a damaged oven would be excessive microwave exposure causing heating of body tissue, not mysterious contamination. Metal objects inside the oven behave in more complicated ways than the simple warning, "Never put metal in a microwave," suggests. Thick, smooth metal containers can reflect microwaves and prevent food from heating properly, while sharp edges, crumpled foil, or narrow points can concentrate electric fields strongly enough to strip electrons from nearby air molecules and create sparks. These electrical discharges may damage the oven, ignite combustible material, or pit the metal surfaces. Yet many microwave ovens already contain metal racks or carefully shaped metallic elements designed to be safe because their dimensions and placement are controlled. The danger depends on geometry, spacing, and field concentration, rather than on metal possessing a universal forbidden property. Ceramics and glass often heat mainly because the food transfers heat into them, but some materials contain minerals, glazes, or moisture that absorb microwaves directly and become unexpectedly hot. A container labeled microwave safe is not necessarily cool after use. It usually means it is unlikely to melt, release harmful substances, crack, or create dangerous electrical behavior under normal microwave conditions. Superheating presents another hidden danger. Very clean water in a smooth container can sometimes be heated above its usual boiling point without forming visible bubbles, because bubbles need small imperfections or particles on which to begin. Disturbing the cup, adding powder, or inserting a spoon can trigger sudden boiling, causing hot water to erupt. This is why heating plain water for excessive periods can be risky even when the surface looks calm. The absence of bubbles does not always mean the liquid is below boiling temperature. Eggs, sealed containers, and foods with skins can also build internal steam pressure until they burst, because microwave energy creates heat faster than vapor can escape. The machine's speed therefore comes with a need for pauses, vents, stirring, and attention to structure. The appliance does not sense flavor, doneness, or safety unless it includes sensors designed to estimate steam, humidity, temperature, or reflected microwave power. The timer merely controls how long energy is supplied. A plate can contain regions hot enough to burn and others cool enough to allow microorganisms to survive, which is why reheated food should be stirred and checked rather than judged only by one warm edge. Beneath all this practicality lies a deeper story about waves and matter. The microwave succeeds because invisible fields can carry energy through space, enter food, and couple selectively to molecular motion. Nothing glowing crosses the chamber. No tiny particles of heat are fired into the meal, and no flame needs to touch the surface. Instead, an electromagnetic pattern fills the metal cavity. Molecules attempt to follow its changing direction, and their imperfect response becomes warmth. What seems like a simple countdown on a kitchen display is actually a controlled conversation between a resonant source, reflected waves, molecular charge, geometry, and time. Your meal becomes hot not because the oven hides fire behind its walls, but because invisible waves are arranged so that matter cannot follow them without slowly turning their order into heat. The hidden quantum pattern. Inside snowflakes and crystals. A snowflake begins as a nearly invisible act of molecular alignment. Yet from that tiny beginning can emerge a six-sided structure so intricate that it looks designed rather than grown. High inside a cold cloud, water vapor encounters a microscopic particle of dust, pollen, or mineral and begins to freeze around it. The first solid arrangement is not random. Water molecules possess a bent shape and uneven electrical charge. So when they lock into ice, they favor a hexagonal crystal structure. This six-fold symmetry becomes the hidden architectural rule behind the branches you later see. The snowflake does not contain a blueprint showing its final form, and no molecule knows where the outer tips will appear. The pattern grows because each new molecule joins the existing crystal according to the quantum structure of chemical bonding and the geometry of the ice lattice. Electron distributions determine how oxygen and hydrogen atoms attract one another. Hydrogen bonds favor particular orientations, and those microscopic preferences repeat across enormous numbers of molecules until an invisible atomic arrangement becomes visible as a six-armed crystal. The word quantum matters here, but not because the snowflake is performing a mysterious trick or existing in several shapes at once. It matters because chemical bonds, molecular shapes, and the allowed energies inside matter are quantum in origin. Classical pictures can describe much of the snowflake's growth once the crystal has formed. But the reason water molecules connect at certain angles and not others reaches back to the quantum behavior of their electrons. The famous symmetry of a snowflake comes from this repeated local rule. Each of the 6 main branches grows outward from the same central crystal and passes through nearly the same surrounding air at nearly the same time. Temperature and humidity change along the falling path, altering how quickly water vapor attaches and whether the crystal develops plates, needles, columns, or elaborate branching arms. Because all 6 sides experience broadly similar conditions, they often develop similar patterns. Yet they are never perfectly identical. One branch may encounter a slightly different concentration of water vapor, a collision with another particle, or a tiny disturbance in airflow. These differences are amplified as growth continues, producing the uniqueness associated with individual snowflakes. The crystal is therefore balanced between order and accident. Its 6-fold framework comes from molecular geometry, while its detailed ornamentation records the changing atmosphere through which it traveled. In this sense, a snowflake is not merely an object falling from a cloud. It is a frozen history of temperature, moisture, and motion. The branching itself is driven by instability. Sharp tips and edges project farther into the surrounding vapor than flat regions do, so they can receive water molecules more efficiently. A small bump grows slightly faster, becoming even more exposed and gathering still more vapor. The difference reinforces itself, causing branches to extend and divide. This process, called diffusion-limited growth, helps explain why delicate patterns can emerge without any central organizer. The surrounding vapor diffuses toward the crystal, and the places best positioned to receive it grow first. Similar principles create branching patterns in frost, mineral deposits, metal solidification, and even some biological structures. Nature often produces complexity, not by issuing detailed instructions, but by repeating simple local interactions under changing conditions. Crystals more generally reveal the same hidden order. When a liquid cools or dissolved material becomes concentrated enough, particles may begin arranging themselves into repeating structures. Salt forms cubic crystals because sodium and chloride ions alternate in a 3-dimensional pattern, shaped by electrical attraction, repulsion, and quantum restrictions. Quartz forms a different structure from silicon and oxygen atoms, producing 6-sided crystal shapes under suitable growth conditions. Diamond and graphite are both made entirely of carbon, yet their atoms connect differently. In diamond, each carbon joins a rigid 3-dimensional network, producing hardness and transparency. In graphite, carbon forms layered sheets that slide more easily, creating softness and electrical behavior unlike diamond. The element has not changed, the pattern has. This is one of the deepest lessons of crystal physics. Matter's properties belong not only to which atoms are present, but to how those atoms are arranged. A crystal is defined by long-range order, meaning its microscopic pattern repeats across distances far greater than a single molecule. This repetition creates special effects. X-rays passing through a crystal scatter from regularly spaced atomic planes, and the outgoing waves reinforce one another only at particular angles. By measuring these patterns, scientists can reconstruct the hidden arrangement of atoms. This method helped reveal the structures of minerals, metals, proteins, and genetic material. The crystal does not need to be opened atom by atom. Its order leaves a signature in the way waves interact with it. The same repeating structure influences how electrons move, how light bends, how heat travels, and how the crystal breaks. A crystal may split cleanly along certain planes because bonds are weaker in those directions. Its optical appearance can change when viewed from different angles because the internal arrangement responds differently depending on the direction of incoming light. Some crystals separate light into 2 rays, rotate the polarization of light, or generate electric voltage when squeezed. Quartz watches use this last effect, called piezoelectricity. Apply voltage to a quartz crystal and it vibrates at a highly stable frequency. Measure those vibrations and they become a reliable clock. The regularity of atomic order is transformed into regularity of timekeeping. Not every solid is a crystal. Glass, Many plastics and some natural materials lack long-range repeating order. Their atoms may be locally connected, but do not continue the same pattern across the entire object. This difference affects how they soften, scatter light, conduct heat, and fracture. A crystal often melts at a fairly specific temperature because its ordered lattice breaks down through a defined transition. An amorphous solid may soften gradually across a range because it has no single repeating structure to dismantle. Even within a crystal, perfection is rare. Real crystals contain vacancies where atoms are missing, impurities where foreign atoms have entered, and dislocations where part of the repeating pattern is misaligned. These defects are not always undesirable. They can determine color, strength, conductivity, and usefulness. Pure corundum is colorless, but tiny amounts of chromium can turn it into ruby. Different impurities produce sapphire in several colors. Semiconductor technology depends on adding controlled defects to crystals, and metal strength can be altered by preventing dislocations from moving easily. Imperfection becomes a design tool. Snowflakes also contain defects, but their beauty survives because symmetry does not require flawless repetition at every scale. The 6 arms can resemble one another, while each remains irregular in detail. This combination is why they feel both mathematical and alive. Their form is constrained, but never fully predetermined. A snowflake's final shape depends on the route it followed through the cloud, and no 2 routes are exactly alike. Even if 2 crystals began with nearly identical centers, tiny differences in air currents and vapor would grow into visible distinctions. The idea that no 2 snowflakes are alike is difficult to prove absolutely for every crystal that has ever existed, especially for very simple snow crystals. But complex snowflakes have so many possible molecular arrangements that exact duplication is extraordinarily unlikely. Their uniqueness is not magical. It is the natural consequence of immense sensitivity to microscopic history. When the snowflake lands on your sleeve, its growth ends as the surrounding conditions change. Warmth disrupts the crystal lattice, and the ordered structure becomes liquid water. The elaborate pattern disappears, yet the molecules remain. What seemed like a permanent object was a temporary arrangement stable only within a narrow range of temperature and humidity. Crystals often appear timeless because their patterns are regular and their shapes can endure, but their order is conditional. Heat, pressure, radiation, chemistry, and time can alter or erase it. And perhaps that is what makes the hidden pattern inside snowflakes and crystals so profound. Their beauty does not come from matter escaping physical law, but from obeying it with extraordinary consistency. Quantum rules shape the bonds. Molecular geometry creates the symmetry. Local conditions guide the growth, and small accidents write the details. From interactions too small to see, nature builds structures large enough to hold in your hand. The snowflake is not designed from the outside. It is order discovering its visible form, one molecule at a time. Why a compass needle obeys invisible quantum rules. A compass needle appears to know where north is, but it has no awareness of maps, continents, or direction. It is simply a carefully magnetized piece of matter, turning until its internal quantum order aligns with a weak magnetic field surrounding the entire planet. The surprising part is that Earth's magnetic field is not especially strong. A small refrigerator magnet can produce a much stronger field nearby. Yet once the compass has moved away from competing magnets, steel objects, electrical cables, and electronic devices, the planet's faint influence is enough to rotate the needle. This happens because the needle has been shaped so that its magnetic moments are largely aligned along its length. Those microscopic moments ultimately arise from the quantum behavior of electrons, especially their intrinsic spin and the way neighboring atoms in certain materials cooperate. In an ordinary unmagnetized piece of iron, many small magnetic regions point in different directions, so their effects mostly cancel. During manufacture, the needle is exposed to a strong magnetic field that encourages a large fraction of those regions to adopt a shared orientation. The material and heat treatment are chosen so that much of this alignment remains after the external field is removed. The finished needle becomes a permanent magnet with 2 poles, and when it is mounted on a low-friction pivot or allowed to float, Earth's field exerts a turning effect on it. The needle does not need to be pulled bodily toward the north. A magnetic field can produce torque, rotating a magnet until its orientation better matches the local direction of the field. Once aligned, opposing tendencies balance and the needle settles, though it may swing back and forth briefly because of its momentum. Friction and air resistance gradually calm the motion. The end marked north is called the north-seeking pole because it points approximately toward geographic north, but the naming hides a subtlety. Opposite magnetic poles attract, so the region near Earth's geographic north pole behaves, in the conventional bar magnet sense, like a magnetic south pole. Scientists usually avoid this confusion by speaking of the north magnetic pole as the location toward which the north-seeking end of a compass points. Even that point is not fixed. It drifts over time because Earth's magnetic field is generated by moving liquid metal deep inside the planet, and that motion continually changes. More than 2,000 kilometers beneath you, Earth's solid inner core is surrounded by a liquid outer core, made largely of iron with other elements mixed in. Heat escaping from the deep interior, chemical changes associated with the slow growth of the inner core, and the planet's rotation help drive complex flows within this electrically conducting liquid. Moving conductive fluid creates electrical currents, and those currents generate magnetic fields. The fields influence the flowing metal in return, producing a self-sustaining process known as the geodynamo. Earth is therefore not a giant permanent bar magnet hidden beneath the crust. If its field came from permanently magnetized iron, the intense temperatures of the deep interior would make that explanation impossible, because ordinary ferromagnetic order cannot survive above certain temperatures. The planetary field is instead produced by moving charge in a restless metallic ocean. Quantum physics makes the iron electrically conductive and gives the compass needle its permanent magnetism, while large-scale fluid motion and electromagnetism create the field the needle follows. Several layers of physics meet in one simple instrument. The compass also does not point toward true geographic north everywhere. Geographic north is defined by Earth's rotation axis, while magnetic north is defined by the planet's changing magnetic field. The horizontal angle between these directions is called magnetic declination. Depending on where you stand, a compass may point several degrees east or west of true north, and the correction changes with location and time. Navigators once had to know this difference carefully, and modern maps may still provide declination information. A compass that works perfectly can therefore guide you in the wrong direction if you assume magnetic north and geographic north are identical. The field is also tilted into or out of the ground. In much of the northern hemisphere, the field points downward as well as northward. In much of the southern hemisphere, it points upward. This angle is called magnetic inclination, or dip. A needle free to rotate vertically would lean rather than remain level. Ordinary compasses are usually balanced for particular geographic zones, so the needle does not drag against its housing. A compass manufactured for one part of the world may perform poorly far away because the vertical pull changes. Global compasses use special designs to tolerate a wider range of field inclinations. This means the needle is responding not to a flat arrow painted across Earth's surface, but to a three-dimensional field curving through the planet and extending far into space. The field resembles that of a tilted dipole only approximately. Real measurements reveal uneven regions, local distortions, and features that change over years. Magnetic minerals in the crust can bend the local direction slightly. Large iron structures, vehicles, tools, reinforced concrete, speakers, and electrical currents can create much larger errors. Even a phone placed beside a traditional compass may disturb it, because the phone contains magnets, current-carrying components, and magnetic materials. A compass is most trustworthy when held level and kept away from such interference. The needle's obedience is not blind loyalty to north. It follows the strongest combined magnetic field at its location. If a nearby magnet overwhelms Earth's field, the compass will turn toward that influence without hesitation. This vulnerability is also what makes the instrument useful. It reveals fields that your body cannot detect directly. Some compasses replace the pivoting needle with electronic magnetometers. Many smartphones use tiny sensors that measure magnetic field components along several directions. These sensors may rely on changes in electrical resistance, microscopic mechanical structures, or other material effects influenced by magnetic fields. Software combines the measurements with data from accelerometers and gyroscopes to estimate heading, even when the phone is tilted. The familiar motion of rotating a phone through a figure-8 pattern helps the device separate Earth's field from internal offsets and nearby magnetic contamination. Yet electronic compasses face the same fundamental problem as the old needle. They measure magnetic north, not an abstract universal direction, and their readings can be distorted by the environment. Earth's field itself has a long and unsettled history. As lava cools, magnetic minerals within it can align with the surrounding field and preserve a record of its direction. By studying rocks on land and the symmetrical magnetic stripes on the seafloor, scientists discovered that Earth's magnetic polarity has reversed many times. During a reversal, the field does not simply switch off and instantly return backward. It becomes more complex and weaker in some regions before reorganizing. There is no reliable evidence that a reversal is imminent merely because the magnetic poles are currently moving, and such changes unfold over geological timescales rather than like a sudden disaster in a single afternoon. The compass needle you watch today follows only the present chapter of a planetary process that has changed repeatedly across Earth's history. It points because electrons inside the needle maintain a collective magnetic arrangement, because liquid metal inside Earth sustains a global field, and because the needle has been given enough freedom to rotate toward the local direction of that field. No invisible line physically grabs its tip, and no signal arrives from the pole telling it where to turn. The surrounding field changes the energy of different orientations, and the needle naturally settles into the one that fits best. What looks like guidance is really alignment. What looks like certainty is only a response to local conditions. And perhaps that is the quiet lesson hidden in the compass. Direction does not live inside the needle. The needle becomes useful because its invisible internal order is sensitive to a larger invisible order around it, allowing a small piece of magnetized metal to translate the restless motion of Earth's deep interior into a direction your eyes can follow. The everyday world is the quiet surface of a quantum ocean. The world around you appears calm, definite, and complete. Yet this familiar stability may be only the quiet surface of a much deeper quantum reality that never presents itself to your senses directly. A cup rests in one place, a door remains either open or closed, and a falling object follows one visible path. So everyday experience encourages you to imagine that nature is built from objects carrying fixed properties at every moment. Quantum theory describes a less intuitive foundation. At microscopic scales, a system can be represented by a combination of possible outcomes rather than by one fully settled classical history, and the mathematical quantities used to describe those possibilities can reinforce or cancel one another like waves. This is not merely uncertainty caused by ignorance, as though a particle had already chosen a hidden answer that better equipment might reveal. Experiments show patterns that depend on the coexistence of alternatives, especially when delicate quantum systems are isolated well enough for their possibilities to remain coherent. Yet you do not see chairs spreading across rooms, cups following several trajectories, or people appearing in overlapping states. The reason is not that quantum rules stop working when an object becomes large. They continue operating within every molecule, but large objects are almost impossible to isolate from their surroundings. Light strikes them, air molecules collide with them, heat escapes from them, and vibrations pass between them and the surfaces nearby. Each interaction carries away information about the object's state and entangles it with the environment. This process is called decoherence. It does not require a conscious observer, and it does not mean human attention magically creates reality. The surrounding world is already monitoring physical systems through countless ordinary interactions. As information spreads into the environment, the delicate relationships that allow distinct quantum alternatives to interfere become effectively inaccessible. The possibilities no longer combine in a way that produces visible interference, and the object begins to behave as though it occupies one ordinary, stable condition. Decoherence happens extraordinarily quickly for large warm objects because they contain huge numbers of particles and interact continuously with everything around them. A small laboratory system may preserve quantum coherence for a measurable time if it is cooled, shielded, and carefully controlled. A macroscopic object in a room loses that isolation almost instantly. Classical reality is therefore not a separate set of laws placed on top of quantum mechanics. It is the large-scale behavior that emerges when quantum systems become deeply connected to their environments. This emergence explains why probability at the foundation does not make daily life chaotic. A single microscopic event may have several possible outcomes, but an ordinary object contains an almost unimaginable number of components. Random variations tend to average out, while stable patterns are reinforced by constant interaction. Temperature, pressure, shape, and motion become reliable collective properties, even though no single particle contains the entire property by itself. A wave on the ocean is real, but no individual water molecule is the wave. In a similar way, solidity, fluidity, and classical motion belong to organized systems rather than to isolated microscopic ingredients. The everyday world is built from patterns that remain dependable because they are supported by vast numbers of underlying events. This is also why quantum physics can be essential without being obvious. A bridge, cloud, animal, and grain of sand all obey quantum laws, but most questions about them are answered more efficiently at higher levels. You do not need to calculate the quantum state of every molecule to predict where a thrown ball will land, just as you do not need to track every air molecule to describe the wind. New descriptions become useful as scale increases. Chemistry emerges from quantum interactions among atoms. Material behavior emerges from chemistry and structure. Biology emerges from complex molecular organization. Thought and experience emerge from living nervous systems. Each level depends on the one beneath it, without being reducible to a simple list of microscopic movements in any practical sense. The higher-level patterns are not illusions. A storm is real, even though it is made from molecules that do not individually contain storminess. A memory is real, even though no single neuron holds the whole experience. Reality can be layered, with each layer possessing meaningful properties that appear only when many parts interact. The metaphor of a quantum ocean is useful if treated carefully. It does not mean empty space is literally filled with a liquid, or that mystical energy flows through every object. It means the stable forms you recognize arise from a foundation described by quantum fields, states, interactions, and probabilities. In modern physics, particles are understood as excitations of underlying fields, and even what appears to be empty space is the lowest energy state of those fields rather than absolute nothingness. Yet the quantum vacuum is not a limitless source of free energy, nor does it allow thoughts to reshape external events at will. Its measurable effects appear under precise physical conditions and remain governed by strict laws. The true strangeness is already profound enough without exaggeration. The universe can produce persistent matter, predictable chemistry, and stable worlds from a foundation that is not made of miniature classical objects behaving exactly like the things you see. Measurement remains one of the deepest unresolved parts of the story. Decoherence explains why interference between large-scale alternatives disappears and why certain stable states are favored by environmental interaction. But interpretations of quantum mechanics disagree about what a single observed outcome ultimately means. Some treat the wave function mainly as a tool for predicting results. Others regard it as a real description of branching possibilities, hidden variables, or information. Experiments strongly constrain these ideas, but no interpretation has achieved universal agreement. Science can calculate quantum outcomes with extraordinary accuracy, while still debating what the mathematics says reality fundamentally is. This is not a weakness unique to quantum theory. It is a reminder that prediction and interpretation are different tasks. A theory may tell you exactly What an experiment will reveal, while leaving open the question of what exists between preparation and observation. The ordinary world seems to answer that question by simply being present. But its certainty may be an emergent achievement rather than a primitive fact. Every stable object has survived continuous interaction with its environment. Every visible shape represents a pattern that has become robust enough to persist. Every classical event is supported by microscopic possibilities whose interference has been dispersed into countless surroundings. You live on the scale where these processes have already produced clear outcomes, so reality arrives looking finished. You see the crest, not the immeasurable activity beneath it. And perhaps this is the final lesson hidden inside the everyday quantum world. Nature is not divided into a strange microscopic realm and a normal human realm. There is only one reality viewed at different scales. The quantum rules remain beneath every ordinary event, but their uncertainty becomes collective stability. Their possibilities become persistent patterns, and their invisible interactions become the world you trust. The room around you is quiet, not because the deeper universe has gone still, but because its complexity has organized itself so completely that the turbulence beneath the surface appears, from where you are, as a table, a window, a breath, and a moment of rest.